Right now, at this exact moment, the moon is abandoning you. It is drifting away from Earth at a velocity of roughly 3.8 centimeters per year, a recession so gentle that it would take 2.5 centuries for the moon to move the length of a single human body farther from the planet where you were born. This departure is invisible. It is imperceptible. A lifetime of moonlit nights will pass without the faintest visible change in that pale disk hanging above the horizon. And yet this glacial retreat has been underway for over 4 billion years, and it will continue for billions more, until the most familiar object in your night sky becomes a stranger, until the geometry of the heavens shifts beyond recognition, until something you have taken for granted since before your species existed vanishes from the human experience forever. In approximately 600 million years, the moon will be too far from Earth to ever again produce a total solar eclipse. This is not speculation. It is not a prediction that might be revised with better data. The mathematics are as certain as the orbit that carries you around the sun. Every revolution of the moon around the Earth adds another 3.8 centimeters to the widening gulf between worlds. Every tide that rises on an ocean beach pushes the moon fractionally farther into space. Every moonrise you witness is the last time the moon will ever be exactly that close to Earth again. Tomorrow night, when the moon climbs above your rooftops and trees, it will be imperceptibly but measurably more distant than it was the night before, and the night before that, and every night stretching back through all of human history to the first ancestor who ever looked up and wondered what that glowing presence in the darkness might be. The departure has been happening since before there were eyes to see it, and it will culminate in an absence that no future generation will ever be able to reverse. If you have ever witnessed a total solar eclipse, you have participated in one of the most improbable coincidences in the known universe. If you have not, you have roughly 600 million years remaining to remedy that oversight, a window of opportunity that sounds impossibly vast until you remember that complex life has already existed on this planet for approximately that same duration, and that the window will close precisely once and never reopen. The moon is leaving. The eclipses are numbered, and though no human being will live to see the final total eclipse, the countdown is already underway, has been underway since the moon formed, and every generation that passes brings the end measurably closer. If you find yourself drawn into this story of cosmic departure, and wish to explore more journeys through the mathematics of time and space, consider subscribing to the channel. Your support makes these expeditions possible. Are you ready? Let us trace the path of the moon's slow goodbye. The relationship between the Earth and the moon began in violence almost beyond comprehension. Approximately 4.5 billion years ago, when the solar system was still a chaotic nursery of half-formed worlds, a planet roughly the size of Mars struck the infant Earth in a collision so catastrophic that it liquefied the surface of both bodies and ejected a ring of molten debris into orbit. This impactor, which planetary scientists have named Theia, after the Greek goddess who was mother to the moon goddess Selene, did not survive the encounter intact. Neither, in a meaningful sense, did the original Earth. What emerged from that cosmic crucible was a new world, heavier and hotter than before, wrapped in an atmosphere of vaporized rock that glowed with the incandescent heat of the collision. And orbiting that wounded planet, coalescing from the ring of debris still bleeding heat into space, was a companion that would remain closer than any other celestial body for billions of years to come. The newborn moon was nothing like the familiar grey presence you know today. It hung in Earth's prehistoric sky at a distance of perhaps 22,500 kilometres, close enough that it would have appeared over 15 times larger than it does now, close enough that it would have dominated the heavens like a second sun painted in shades of molten orange and cooling grey. The Earth rotated far more rapidly in those early eons, completing a full day in perhaps 5 or 6 hours, and the enormous moon looming overhead raised tides in the still molten surface that stretched the planet's rock like taffy. The gravitational interaction between these two worlds was not gentle. It was a constant grinding exchange of energy that shaped both bodies as they spiraled slowly away from each other through the dark. This is the mechanism you must understand to grasp why the moon is leaving, and why nothing can stop it, and why the departure was inevitable from the first moment the moon existed. Imagine the Earth rotating beneath its companion like a top spinning under the watchful gaze of a nearby weight. The moon's gravitational pull raises bulges in the Earth, one on the side facing the moon, and one on the opposite side, creating the familiar phenomenon of the tides. But the Earth rotates faster than the Moon orbits. This means the tidal bulge is carried ahead of the Moon by the planet's rotation, pulled forward like a dog straining at a leash. The bulge leads the Moon by a small angle, and because mass exerts gravitational attraction, that leading bulge pulls forward on the Moon ever so slightly, adding energy to its orbit. An orbit with more energy is a wider orbit. The Moon climbs higher. Meanwhile, the Moon's gravity pulls backward on the leading tidal bulge, creating drag on the Earth's rotation. The planet slows. Energy bleeds from the spin of the Earth into the orbit of the Moon, and the consequence of this transfer has been playing out for 4.5 billion years. When the Moon first formed, it may have orbited the Earth once every few hours. Today it takes 27.3 days. The Earth's rotation has slowed from those frantic 5-hour days to the stately 24 hours you experience now. Both changes are manifestations of the same ongoing transaction, the same patient redistribution of angular momentum from a spinning planet to a climbing Moon. The rate of this retreat is not constant across geological time. When the Moon was closer, the tidal forces were stronger, and the recession happened faster. As the distance increased, the gravitational coupling weakened, and the drift slowed accordingly. 4 billion years ago, the Moon might have been receding at a rate of several meters per century. Today, that rate has diminished to 3.8 centimeters per year, a measurement so precise that scientists can verify it to within a fraction of a millimeter. This verification comes from one of the most elegant experiments ever left on the surface of another world. Between 1969 and 1972, Apollo astronauts deployed 5 retroreflector arrays on the lunar surface, panels of precisely machined corner-cube prisms designed to bounce incoming light directly back toward its source regardless of the angle at which the light arrives. These reflectors require no power, no maintenance, no active components of any kind. They simply wait, patient and unchanging, for a signal from Earth. The signal comes in the form of laser pulses fired from observatories on Earth, beams of coherent light aimed with exquisite precision at targets roughly 384,000 kilometers away. When a pulse strikes a retroreflector and bounces back, sensitive detectors on Earth record the return signal and measure the round-trip travel time to within a few hundred trillionths of a second. Since light travels at a known, constant velocity, that timing measurement can be converted into a distance measurement accurate to within a centimetre. Month after month, year after year, decade after decade, observatories around the world have fired lasers at the Moon and measured the returning echoes. The data accumulated over more than 50 years tells an unambiguous story. The Moon is receding at 382 centimetres per year, plus or minus a few millimetres. This is not a theoretical prediction awaiting confirmation. It is a measurement, repeated thousands of times, consistent to remarkable precision, verified by independent observatories on multiple continents. The Moon is leaving, and we know exactly how fast. To translate this into terms more immediate to human experience, consider what the measurement means for a single human lifetime. If you are fortunate enough to live 80 years, the Moon will move approximately 3.25 meters farther from Earth, between your birth and your death. This is a distance you could cross in 2 unhurried steps. If you extended your arms to their full span, the Moon's lifetime retreat would measure roughly 1.5 times your reach. The entire arc of your existence, all your memories and experiences, and the complete history of everyone you will ever love will unfold while the Moon drifts slightly more than the height of a single story in an ordinary building. This seems absurdly, almost insultingly small. What could possibly matter about a change so minuscule, a recession so imperceptible that no human eye could ever detect it? The Moon looks exactly as it looked to your grandparents, exactly as it looked to the scholars of ancient Alexandria, exactly as it looked to the nameless artists who painted bison and deer on cave walls 40,000 years ago. The geometry of your sky is essentially unchanged across the entire span of human civilization. Whatever cosmic departure is underway seems to be operating on a timescale so vast that it might as well be infinitely distant, might as well be someone else's problem, might as well be nothing at all. But consider the compound interest of deep time. In 100,000 years, the Moon will be roughly 4 kilometers farther away than it is tonight. This is a trivial distance by cosmic standards, barely perceptible against the enormous baseline of the lunar orbit, yet it represents the passage of more time than all of recorded human history multiplied by a factor of 12. Civilizations rose and fell, empires conquered and crumbled, writing was invented and literature flowered and science reshaped the understanding of reality. And through all of it, the moon drifted 4 kilometers farther into the dark. In 1 million years, the moon will be approximately 38 kilometers more distant. Now we are speaking of a span of time during which the human species itself has undergone substantial evolution, during which ice ages have come and gone repeatedly, during which the geography of continents has shifted perceptibly, coastlines redrawing themselves as sea levels rose and fell with the glacial cycles. 1 million years ago, your ancestors were just beginning to master fire and shaped stone. 1 million years from now, whatever descendants you may leave will inherit a moon that has climbed another 38 kilometers into the sky, and the process will still be underway. In 100 million years, the moon will be roughly through 800 kilometers farther from Earth than it is now. This is approximately the distance from New York to Los Angeles, the width of the continental United States, a span that seems modest until you remember that the moon's current average distance is approximately 384,400 kilometers. Even a retreat of 3,800 kilometers represents less than 1% of that total distance. But 100 million years is a span in which species originate and go extinct, in which continents drift and oceans are born and mountain ranges rise and erode away. 100 million years ago, dinosaurs dominated the Earth, and the first flowering plants were only beginning their explosive radiation. The future of 100 million years is as alien and unknowable as the Cretaceous period, and in 600 million years the retreat will reach a threshold from which there is no return. The moon will still be there. It will still be the brightest object in the night sky after the sun itself. It will still raise tides, though more weakly than today. It will still wax and wane through its familiar phases, still inspire poets and guide travellers who navigate by its light. But the delicate geometry that creates total solar eclipses will have broken down beyond repair, and the last human being capable of standing in the moon's shadow on an eclipse day will have died hundreds of millions of years before the final eclipse occurs. To understand why, you must understand what a total solar eclipse actually requires. A solar eclipse happens when the moon passes directly between the Earth and the Sun, blocking some or all of the solar disk from view. This alignment is not unusual. Because the moon orbits Earth and Earth orbits the Sun, the three bodies line up roughly every month at the new moon phase. But the moon's orbit is tilted by about 5 degrees relative to Earth's orbit around the Sun, which means that on most new moons the moon passes slightly above or below the Sun from Earth's perspective. Only when the new moon occurs near one of the 2 points where the lunar orbit crosses the plane of Earth's orbit, points called the nodes, does an eclipse become possible. Even then, not all solar eclipses are total. The Sun is roughly 400 times the diameter of the moon, but it is also roughly 400 times farther away from Earth. This cosmic coincidence means that the Sun and the moon appear almost exactly the same size in Earth's sky, each spanning approximately half a degree of arc, about the width of your little finger held at arm's length. When the moon is slightly closer in its orbit and the Sun is slightly farther, the moon appears large enough to completely block the solar disk, and observers in the moon's shadow experience the astonishing phenomenon of totality: the Sun's blazing surface hidden behind lunar rock, the delicate corona streaming into suddenly darkened skies, stars appearing in daytime, the temperature dropping, animals falling silent as though night had come without warning. But when the moon is slightly farther in its orbit and the Sun is slightly closer, the moon's apparent size shrinks below that of the Sun. The lunar disk cannot fully cover the solar disk. A ring of brilliant sunlight remains visible around the moon's silhouette, creating what astronomers call an annular eclipse, from the Latin word annulus, meaning ring. The corona remains invisible, overwhelmed by the unblocked solar surface. The sky does not go dark. Stars do not appear. The profound strangeness of totality gives way to a merely impressive astronomical curiosity. The difference between these two experiences is not subtle. Totality is often described by those who have witnessed it as the most profound natural phenomenon accessible to human perception, an event that rewires the brain's understanding of its place in the cosmos. Annularity is interesting, worth travelling to see, but fundamentally different in kind. One transforms, the other merely impresses, and the difference depends entirely on whether the moon appears large enough in the sky to fully occlude the sun. As the moon recedes from Earth, its apparent size shrinks. This is simple geometry. An object seen from farther away subtends a smaller angle in the visual field. Every year, as the moon climbs 3.8 centimetres higher in its orbit, it appears fractionally smaller from Earth's surface. Today the moon's angular diameter varies between about 29.4 and 33.5 arc-minutes, depending on where the moon is in its elliptical orbit. The sun's angular diameter varies between about 31.5 and 32.5 arc-minutes. Because the ranges overlap, sometimes the moon appears larger than the sun, and sometimes smaller, which is why some eclipses are total and others are annular. But the overlap is narrow, and it is shrinking. Every century, the moon's average apparent size decreases by approximately 0.02 arc-minutes. This sounds infinitesimal, and over human timescales it is. But over millions of years, over tens of millions of years, over hundreds of millions of years, the cumulative change adds up. The moon's apparent size will eventually fall below the sun's minimum apparent size. When that happens, totality will become impossible. No point in the moon's orbit will bring it close enough to appear larger than even the smallest sun. Annular eclipses will continue for a time, the ring of fire growing wider and wider as the moon's disk shrinks relative to the sun's. And eventually, as the recession continues, even annular eclipses will become marginal events, the moon barely biting into the solar disk at best, until finally even partial eclipses worthy of notice will be events of the deep geological past. The calculations suggest that the last total solar eclipse visible from Earth will occur in approximately 600 to 650 million years, depending on the precise rate of lunar recession and the complex variations in both the moon's and Earth's orbits over such immense timescales. This estimate contains uncertainties, as all projections into deep time must, but the underlying trajectory is not in doubt. The moon is retreating. Total eclipses require a specific size ratio. The ratio is changing in the wrong direction. The conclusion is inescapable. You're living in a privileged window of cosmic time, a window that opened when the moon receded far enough from its original formation distance to establish something like its present apparent size, and a window that will close when it recedes past the critical threshold. The window is approximately 1 billion years wide. Compared to the eventual lifespan of the Sun, this is a substantial fraction of solar system history. Compared to the lifespan of a human being, or of human civilization, or even of the human species, it is functionally eternal, but it is not infinite. The clock is running, and every year the window narrows by another 3.8 centimetres. There is something deeply strange about contemplating the loss of a natural phenomenon that will not disappear for hundreds of millions of years. The emotional register is unfamiliar. It is not grief, exactly, because the loss is too far in the future to mourn. It is not urgency, because there is nothing to be done and no deadline that any living person needs to meet. It is not indifference, because once you understand what is happening, indifference becomes impossible. Perhaps it is closest to the feeling of holding an hourglass with a 1,000-year supply of sand and watching the first few grains tumble through the neck. You know how this ends. You know you will not be there to see it. But you cannot look away, and you cannot quite stop counting. The most disorienting aspect of lunar recession is not the vastness of the timescales involved, though those timescales defy intuition at every turn. It is the fact that you can almost feel it happening. Human beings are not accustomed to perceiving geological processes directly. Continental drift operates at roughly the speed of fingernail growth, too slow for the eye to detect, too slow even for the lifespan of civilizations to make visible. Mountain ranges rise over tens of millions of years, imperceptible increments of uplift buried in the noise of earthquake and erosion. The sun is gradually brightening as it fuses hydrogen in its core, increasing in luminosity by approximately 1% every 100 million years. But no human being has ever noticed the sun getting brighter, because the change is lost in the daily and seasonal variations that dwarf it by orders of magnitude. But the moon recedes by 3.8 centimetres per year. This is a number you can hold in your hand. If you placed your thumb and forefinger 3.8 centimetres apart, you would be spanning the annual retreat of the moon from Earth. The distance is smaller than a tennis ball, It is roughly the length of an adult's middle finger from tip to first knuckle. It is the width of a matchbox, the diameter of a golf ball, the thickness of a modest paperback novel. You can see 3.8 centimetres. You can measure it with a ruler you already own. You can walk 3.8 centimetres in less time than it takes to blink. This is what makes lunar recession uniquely accessible among geological phenomena. You cannot see continental drift. You cannot see mountain building. You cannot see the sun brighten or the stars wheel through their proper motions or the cosmic microwave background redshift as the universe expands. But you can see 3.8 centimetres. You can point to it. You can say, that is how far the moon moved this year. That is the size of the departure. That is the measure of what we are losing. And because you can see it, you can compound it. Every year, another 3.8 centimetres. Every decade, another 38 centimetres, just over a foot, the length of a typical sheet of paper. Every century, another 3.8 metres, roughly the height of a ceiling in a generously proportioned room. Every millennium, another 38 metres, the length of an Olympic swimming pool. These are not abstractions. These are distances you know, distances you have walked and swum and crossed in the ordinary course of living. The moon's retreat is calibrated in units that belong to human experience, even as the cumulative retreat exceeds anything human experience can contain. When the Great Pyramid of Giza was built, approximately 4,500 years ago, the moon was roughly 171 metres closer than it is tonight. This is the length of nearly 2 American football fields. If you could somehow freeze the moon at its current position and then stack all the retreat it has accomplished since Khufu's architects laid the first foundation stones, you would produce a tower of space taller than the Washington Monument. When anatomically modern humans first emerged in Africa, perhaps 300,000 years ago, the moon was approximately 11.4 kilometres closer to Earth. This is the distance of a respectable walk, an hour or two of brisk hiking, closer than many suburban commutes. In the time since the first beings who were recognisably human looked up at the sky and wondered what they saw, the moon has retreated farther than you could throw a ball, farther than a bow could shoot an arrow, farther than the first rockets could fly. When the dinosaurs went extinct 66 million years ago, the moon was approximately 2,500 kilometres closer than it is now. This is roughly the distance from London to Cairo, from New York to Denver, from Tokyo to Bangkok. In the time since an asteroid ended the Mesozoic era and cleared the way for mammals to inherit the Earth, the moon has receded by a distance greater than the width of Greenland, and this retreat has consequences beyond the eventual loss of total eclipses. The same tidal interaction that pushes the moon away is slowing the rotation of the Earth, gradually lengthening the day. When the moon first formed, Earth's day was perhaps 5 or 6 hours long. 1 billion years ago, the day was approximately 18 hours. 500 million years ago, when the first complex animal life was just beginning to colonize the land, a day lasted about 21 hours. Today it lasts 24 hours. And in the deep future, as the moon continues to recede and the tidal breaking continues to slow Earth's spin, days will grow longer still. Eventually, hundreds of billions of years in the future, the Earth and Moon will reach a state called tidal locking, where the same face of Earth always points toward the Moon, and the same face of the Moon always points toward Earth. A day on Earth will equal a month, both lasting approximately 47 of our current days. The Moon will hang motionless in the sky for half the planet, and remain forever invisible from the other half. The tides will cease. The slow dance of recession will end. But this future is so distant that the sun will have long since exhausted its hydrogen fuel and expanded into a red giant, likely engulfing or at least scorching the inner solar system into unrecognizability. The tidal locking of the Earth-Moon system is not a future that any terrestrial descendant will witness. What matters for the present moment, for the next few 100 million years at least, is that the recession is ongoing and the consequences are real. The days are getting longer by approximately 1.4 milliseconds per century, a lengthening so slight that it would take 70,000 years to add a single second to the day. But atomic clocks can measure this change, and the historical record of ancient eclipse observations confirms it retrospectively. Solar eclipses recorded by Babylonian astronomers and Chinese court historians occurred at times slightly different from what calculations based on the current length of day would predict. The discrepancy is explained by the gradual slowing of Earth's rotation. The past rotated faster, the future will rotate slower, and the Moon, the author of this deceleration, will continue to climb away from the planet it is slowing down. There is a poetry to this exchange, even if the poetry is tinged with melancholy. The Earth is trading its spin for the Moon's distance. Every high tide that rises on a shoreline extracts a tiny fraction of a moment from the turning of the world, and transfers it to the orbit of the departing companion. The tides themselves, those rhythms of rise and fall that have shaped coastlines and dictated the behaviours of countless marine organisms for billions of years, are the mechanism of the Moon's departure. The very thing that binds the Earth and Moon together in gravitational embrace is also the thing that drives them apart. The Moon we see tonight is not the Moon that hung over the early Earth. It is not the Moon that will hang over the Earth 600 million years hence. It is a specific Moon, at a specific distance, producing specific eclipses, governing specific tides, belonging to a specific epoch in a story that began in fire and will end in separation. And you are here now, in this particular moment of that story, watching the departure unfold at 3.8 centimetres per year, close enough to almost feel it happening, too slow to do anything but witness. The earliest humans who studied the Moon had no conception of this departure. To them, the Moon was eternal, unchanging, a perfect sphere of divine light that had always been and always would be. The Greek philosophers debated whether the Moon was made of fire or air, or some celestial element unknown on Earth. The Babylonians tracked its phases with obsessive precision, building vast tables of lunar positions that allowed them to predict eclipses centuries in advance. Medieval European scholars argued about whether the Moon's spots were clouds in a lunar atmosphere or imperfections in what was supposed to be a perfect heavenly body. In no tradition, in no culture, in no system of ancient or medieval astronomy did anyone suspect that the Moon was receding, that its distance was variable on cosmic timescales, that the familiar lantern of the night sky was slowly but inexorably climbing away into the dark. The discovery that the Moon was receding is a triumph of modern physics, a consequence of understanding that the universe operates according to laws that can be expressed in mathematics and tested against observation. Isaac Newton's theory of gravitation, published in 1687, provided the conceptual framework. The tides, Newton demonstrated, are caused by the gravitational pull of the Moon and the Sun raising bulges in Earth's oceans. The Moon pulls harder on the water facing it than on the solid Earth beneath, stretching the ocean toward the Moon. On the far side, the Earth itself is pulled toward the Moon more strongly than the distant water, leaving a second bulge behind. 2 high tides per day, 2 low tides per day, the eternal rhythm explained at last by mathematics. But Newton's equations also implied something he did not explore. The tidal interaction transfers energy. The realization that this transfer would cause the Moon to recede emerged gradually over the following centuries, as astronomers refined their understanding of celestial mechanics and physicists developed the concept of conservation of angular momentum. By the mid-20th century, the recession was theoretically certain. By the late 1960s, with retroreflectors on the lunar surface and lasers capable of hitting them, the recession became measurable. The Moon's departure was no longer a deduction from equations. It was a number, precise to the millimetre, confirmed by light travelling across the void and returning with the answer embedded in the timing of its echo. You live in the first era of human history when the Moon's departure can be not merely predicted but measured, not merely calculated but verified. Your ancestors looked at the Moon and saw permanence. You look at the Moon and know it is leaving. This is the gift and the burden of scientific understanding. The cosmos is not a backdrop painted for human benefit, but a system evolving according to rules that care nothing for human wishes or human timescales. The Moon recedes whether you observe it or not. The eclipses will end whether you mourn them or not. The universe does what the laws of physics require, and the laws require that the Moon climb forever higher until the geometry that creates totality breaks down beyond repair. There is, however, a strange consolation hidden in this certainty. The same physics that guarantees the end of total eclipses guarantees that you are witnessing them now. The same tidal interaction that is pushing the Moon away is the reason the Moon exists in the stable orbit that makes eclipses possible in the first place. Without the tidal transfer of angular momentum, without the gradual recession that has been underway for billions of years, the Earth-Moon system would have evolved differently, and there is no guarantee that the result would have produced eclipses at all. The very coincidence that makes total solar eclipses possible, the nearly exact apparent sizes of the Sun and Moon, is not a permanent feature of the solar system, but a transient configuration, a snapshot of a dynamic process caught at a particular moment. If the Moon had remained at its original post-formation distance, it would have appeared far larger than the Sun, blocking not just the solar disk but also the corona, creating total eclipses that would have been impressive but lacked the otherworldly beauty of the corona streaming into darkened skies. If the Moon had never formed at all, if Theia had missed, or the debris had failed to coalesce, Earth would have no natural satellite, no monthly phases to mark the passage of time, no tides worth mentioning, and certainly no eclipses of any kind. The fact that you can witness a total solar eclipse, the fact that such a phenomenon exists at all, is not a given but a gift, a consequence of the specific history of this solar system and the specific point in that history at which you happen to exist. You are here, watching the Moon leave, because the Moon exists, and because the Moon's recession has brought it to the distance where eclipses work the way they do. An earlier observer, had intelligence arisen sooner in Earth's history, would have seen larger lunar disks and more frequent but less aesthetically perfect eclipses. A later observer, hundreds of millions of years hence, will see only annular and partial eclipses, the corona forever hidden behind unblocked solar light. But you, living in this particular geological moment, have access to something that required billions of years to arrange, and will be impossible to recapture once lost. The window is open. Step through it while you can. Every total solar eclipse that remains in Earth's future is, in a sense, numbered. Astronomers can calculate eclipse paths for millennia in advance, and though the accuracy of such predictions decreases over time as small uncertainties compound, the near-term future is well mapped. In your lifetime, depending on when you were born and how long you live, perhaps 3 or 4 dozen total eclipses will occur somewhere on Earth's surface. Most will trace their paths over oceans or uninhabited wilderness, accessible only to those willing to travel to remote locations and hope for clear skies. A few will cross populated regions, offering millions of people the chance to experience totality without extraordinary effort. The total solar eclipse of April 8, 2024, crossed North America from Mexico to Canada, offering approximately 32 million Americans the chance to experience totality without leaving their home communities. The total solar eclipse of August 12, 2026, will cross Greenland, Iceland and Spain. The total solar eclipse of August 2027 will traverse North Africa and the Arabian Peninsula. The total solar eclipse of July 22, 2028, will sweep across Australia and New Zealand. These dates are certain. These paths are calculated. The geometry of the Earth-Moon-Sun system allows prediction with exquisite precision. But beyond the near term, beyond a few centuries of confident projection, the details blur into statistical ranges and probabilistic estimates. What can be said with certainty is that total eclipses will continue to occur, will continue to trace their narrow paths across Earth's surface, will continue to offer those who seek them out the chance to stand in the Moon's shadow and witness the cosmos in a way that no other experience quite equals. And then, gradually, imperceptibly at first, but inevitably as the eons pass, the totality will narrow. The duration of totality at maximum eclipse will shrink. The geographical bands in which totality is visible will narrow. The corona will become harder to see as the Moon's disk leaves ever more of the solar surface unblocked at the edges. And finally, perhaps 620 million years from now, perhaps 650 million years, perhaps a bit sooner or later depending on factors too numerous and too uncertain to calculate precisely, the last total eclipse will occur. A narrow path will trace across a world that no human eye could recognize as Earth, a world whose continents have merged and drifted and re-merged in patterns no one can foresee, a world whose climate and ecosystems have transformed beyond imagination. If there are observers there, if some descendant of terrestrial intelligence has survived the intervening eons, or if some new intelligence has arisen to take our place, they will see something never to be repeated. The last moment when the Moon appears large enough, at the right point in its orbit to fully occlude the Sun. And then it will be over. The Moon will continue to recede. The Sun will continue to shine. But the specific, improbable, temporary configuration that creates totality will have slipped beyond the boundary of the possible, and no technology, no intervention, No act of will or ingenuity will ever be able to bring it back. The eclipse will end, the window will close, the moon's slow goodbye will reach the point where a particular kind of wonder becomes extinct. This is the knowledge you carry now, standing on a planet where the moon is still close enough to matter, watching a companion that has been with you since before there was a you to watch. The moon is leaving. It will not return. And the time you have to see what it can do is vast by human measure but finite by cosmic accounting. What you choose to do with this knowledge is your own affair. The mathematics of lunar recession is ancient, but our understanding of its mechanism is surprisingly modern. For most of human history, the moon's slow retreat was not merely unknown, but inconceivable. The celestial spheres seemed permanent, fixed in their courses by divine decree or cosmic necessity. The moon rose and set, waxed and waned, pulled the tides and marked the months, and no one imagined it might be creeping away, centimetre by centimetre, into the darkness. The first hint that something dynamic was occurring came not from astronomers, but from those who studied the tides themselves. The rhythm of the oceans has always been tied to the moon, a connection recognised since antiquity. Aristotle noted it. Pliny the Elder documented it. Sailors and fishermen have understood it in their bones for as long as humans have worked the waters. But the full story of what the tides are doing, what they cost the Earth-Moon system, what they imply about the deep future, required a revolution in physics that would not come until the late 17th century. Isaac Newton, working in the relative isolation of his family's estate at Woolsthorpe during the plague years of 1665 and 1666, laid the foundation. His theory of universal gravitation explained the tides as a consequence of differential gravitational attraction. The moon pulls on the Earth, but it pulls harder on the near side than on the far side, and this difference in pull creates a stretching effect. The ocean, being fluid, responds to this stretching by bulging outward, both toward the moon and away from it. The Earth rotates beneath these bulges, and we experience their passage as the rise and fall of tides. This much was understood by Newton's contemporaries and successors. But the deeper implications, the energetic cost of this tidal interaction, remained obscure for another 2 centuries. The key insight came from George Howard Darwin, the 5th child of Charles Darwin, and himself a distinguished astronomer and mathematician. In the 1870s and 1880s, the younger Darwin turned his attention to the problem of tidal evolution, applying the mathematical tools of his era to questions about the Earth-Moon system's past and future. What Darwin recognised was that the tidal bulges raised on Earth by the moon do not point directly toward the moon. They are dragged slightly ahead of the moon's position by Earth's rotation. The Earth spins once every 24 hours. The moon orbits once every roughly 27 days. Because the Earth's rotation is faster than the moon's orbital motion, the tidal bulges are carried forward, displaced from the line connecting Earth's centre to the moon's centre. This displacement is small, perhaps a few degrees, but its consequences are profound. The displaced bulges create an asymmetry. The near side bulge, being slightly ahead of the moon, exerts a gravitational pull that tugs the moon forward in its orbit. This forward tug accelerates the moon, and here is where orbital mechanics delivers its counterintuitive verdict. An object that is accelerated in its orbit does not speed up. It moves outward, to a higher orbit, where it actually moves more slowly. The energy transferred to the moon by the tidal bulge lifts it into a larger orbit. The moon gains orbital energy and angular momentum. It recedes, but energy is conserved. The energy the moon gains must come from somewhere, and it comes from Earth's rotation. The same gravitational interaction that accelerates the moon exerts a braking torque on the Earth. The tidal bulges, dragged forward by Earth's spin, are pulled backward by the moon's gravity. This backward pull acts as a brake on Earth's rotation. The planet slows down. The days grow longer. This is not metaphor. This is measurement. The length of Earth's day is increasing by approximately 1.4 milliseconds per century. This rate seems trivial, a rounding error in the vast ledger of cosmic time. But it is also relentless. It has been operating for billions of years. It will continue for billions more, and its cumulative effect has already transformed the Earth-Moon system beyond recognition. The moon's current recession rate, 3.8 centimetres per year, represents the ongoing hemorrhage of Earth's rotational energy into the moon's orbital energy. The energy dissipated in the tides, the friction of seawater sloshing against continental shelves and churning through shallow seas, amounts to approximately 3.1 terawatts. This is roughly 1/6 of humanity's total power consumption, a significant fraction of a civilization's energy budget, being continuously expended simply to maintain the rhythm of the tides. And this energy, once dissipated as heat in the oceans, is gone from the Earth-Moon system's rotational budget forever. The relationship between tidal dissipation and lunar recession creates a profound connection between geography and astronomy. The rate at which the Moon recedes depends on where the continents are positioned and how the ocean basins are configured. Shallow seas are more efficient at dissipating tidal energy than deep oceans. Coastlines that funnel and concentrate tidal flows, like the Bay of Fundy with its legendary tides, contribute disproportionately to the total energy loss. The specific arrangement of Earth's land masses at any given moment in geological history determines how fast the Moon is moving away. This is why the current recession rate cannot simply be extrapolated backward into deep time. If the Moon had always been receding at 3.8 centimeters per year, simple arithmetic places its formation only about 1.5 billion years ago. But we know from multiple independent lines of evidence that the Moon is approximately 4.5 billion years old, essentially the same age as the Earth itself. This discrepancy, sometimes called the Gersten-Korn event problem after the German astronomer who first analysed it carefully, tells us that the recession rate must have varied dramatically over Earth's history. And indeed it has. Computer models of ancient ocean tides, constrained by paleomagnetic reconstructions of past continental positions, suggest that the current rate is unusually high. During periods when the continents clustered together into supercontinents, the oceans were more open and circular, and tidal dissipation was less efficient. The Moon's retreat slowed. During periods of continental dispersal, with complex coastlines and shallow seas, dissipation increased. The Moon retreated faster. The rate has oscillated, sometimes by factors of 2 or 3, throughout Earth's history. We can confirm this variation through multiple independent measurements. The most direct comes from ancient tidal rhythmites, sedimentary deposits laid down by tidal cycles millions or billions of years ago. These deposits preserve daily, monthly, and annual layering patterns that can be counted like tree rings. By analysing the ratio of daily to monthly to annual layers, paleontologists can reconstruct how many days there were in a month and how many days in a year when the sediments were deposited. The results are striking. Tidal rhythmites from the Wheelie Wally Formation in Australia, approximately 2.45 billion years old, indicate that the day length then was approximately 17 hours. Rhythmites from the Big Cottonwood Formation in Utah, roughly 900 million years old, suggest a day length of around 18.9 hours. Fossils of ancient corals, which lay down daily and annual growth bands, tell a similar story. Devonian corals from 380 million years ago show approximately 400 daily growth bands per annual cycle, implying a year of 400 days and a day length of about 22 hours. The evidence is consistent and compelling. The Earth is slowing down, the days are lengthening, the Moon is retreating, and these three phenomena are linked by the iron laws of physics, as certain as gravity itself. But understanding the mechanism is only the beginning. The full story of lunar recession requires grappling with timescales that stretch the human imagination to its breaking point and demand a kind of temporal humility that does not come naturally. You must somehow hold in your mind the knowledge that the Moon you see tonight, hanging serene in the evening sky, is not the same Moon your ancestors saw, is not the same Moon the dinosaurs saw, is not the same Moon that illuminated the first protocontinents emerging from the primordial ocean. It has changed. It is changing. It will continue to change. And the changes, though invisible on human timescales, are as real and as measurable as the distance from your house to the corner store. Consider what the Earth-Moon system looked like when the dinosaurs walked the planet, 65 million years ago at the end of the Cretaceous period. The Moon was closer then, perhaps 2,500 kilometres closer if we assume the current recession rate, though the actual distance is uncertain due to variations in tidal dissipation. The Moon appeared perhaps 1% larger in the sky. Total solar eclipses lasted fractionally longer at maximum. The tides were slightly higher. The days were perhaps 20 minutes shorter. These differences are subtle, perhaps too subtle to notice even if you could somehow transport yourself back to that world. A Cretaceous observer, if such could exist, would find the Moon familiar. The the same Maria, the same bright highlands, the same face turned permanently earthward. But the differences are there, embedded in the geometry, measurable in principle even if imperceptible in practice. Go back further. Go back to the Cambrian explosion, 540 million years ago, when complex animal life first burst onto the scene in an evolutionary frenzy that transformed the planet's biology forever. The Moon was closer still, perhaps 20,000 kilometres closer than today, orbiting the Earth every 25 days or so rather than 27. The days were roughly 21 hours long. A year contained about 420 days. The tides were more powerful, perhaps 20% higher than today's tides, scouring the shallow seas where the first trilobites crawled and the first shelled creatures left their marks in the sediment. Still, the differences remained subtle by human standards. You would recognise the Moon. You would know the tides. The sky would feel familiar even as the world beneath it would seem alien beyond comprehension. But continue backward. Go back to the Precambrian eons, to the time before complex life, before the oxygenation of the atmosphere, before the Earth settled into anything resembling its current state. Go back 2.5 billion years to the era of the Wheelie-Wally rhythmites. Now the differences become dramatic. The Moon hung much closer, perhaps 52,000 Earth radii from Earth's centre, compared to 60.3 Earth radii today. It appeared perhaps 15% larger in the sky, a genuinely noticeable difference. More importantly, the tides it raised were dramatically more powerful. Tidal forces scale with the inverse cube of distance. A Moon 15% closer raises tides not 15% larger, but roughly 50% larger. The shallow seas of the Archean Earth churned with tidal flows that would seem violent by modern standards. And the days were barely 17 hours long. The Earth spun much faster, completing more than 500 rotations in each orbit around the Sun. The rapid rotation had consequences for weather patterns, for ocean circulation, for the distribution of heat across the planet's surface. The world was fundamentally different, shaped in part by its faster spin and closer Moon. Go back further still. Go back 4.5 billion years to the aftermath of the Moon's formation. Here the story becomes truly extraordinary. The leading theory for the Moon's origin, developed in the 1970s and 1980s and now supported by substantial evidence, holds that the Moon formed from a catastrophic collision between the early Earth and another planetary body roughly the size of Mars. This impactor, sometimes called Theia, struck the Earth at an oblique angle with a velocity of several kilometres per second. The collision was among the most violent events in solar system history, releasing enough energy to completely melt Earth's surface and vaporise much of both bodies. The debris from this collision, a disk of molten and vaporised rock orbiting the ravaged Earth, coalesced within perhaps a few centuries into the body we call the Moon. And this newborn Moon formed close, very close. Different models give different estimates, but many suggest the Moon initially orbited perhaps 20,000 to 30,000 kilometres from Earth's surface, compared to nearly 385,000 kilometres today. The Moon filled the sky, a bloated orange-red disk many times larger than it appears now, glowing with the heat of its own formation. The tides this close Moon raised were apocalyptic by any subsequent standard. Tidal forces scaling with the inverse cube of distance. A Moon 10 times closer raises tides 1,000 times more powerful. The Earth's molten surface was pulled and stretched by these forces. The days, lasting perhaps only 5 or 6 hours, blurred into a continuous cycle of light and dark almost too rapid to comprehend. The Earth rotated so fast that it bulged noticeably at the equator, its shape distorted by its own spin, and from the very first moment after the Moon's formation, the recession began. The same mechanism operating today, tidal bulges dragged ahead by Earth's rotation, transferring angular momentum to the Moon, was operating then, but vastly more intensely. The recession rate in those earliest days was not centimetres per year, but metres per year, perhaps tens of metres per year. The Moon spiralled outward with a speed that would be visible on human timescales if humans had existed to observe it. This rapid early recession slowed as the Moon moved outward. The tidal forces weakened, the energy transfer decreased, the recession rate dropped. By the time Earth had cooled and oceans had formed, perhaps a few 100 million years after the impact, the recession had slowed to perhaps 10 or 20 centimetres per year. By the time the first cells emerged, it had slowed further. The history of lunar recession is a history of deceleration, of a process that began in catastrophic violence and has been settling toward equilibrium ever since. We carry evidence of this history in our planet's rocks, in the length of our days, in the height of our tides. The Earth-Moon system is not static. It never was. The serene moon rising over the ocean, seemingly eternal and unchanging, is a snapshot of a dynamic process, a frame from a movie billions of years long. Understanding this history changes how you see the night sky. The moon becomes not a fixture but a traveller, not a constant but a variable, not an eternal companion but a departing one. Every moonrise becomes a small farewell, a moment in a goodbye that has been ongoing since before the continents existed, and will continue until long after they have merged and split and merged again beyond recognition. But the past, however dramatic, is fixed. What captures the imagination and troubles the spirit is the future, the long continuation of this recession into eons yet to come, and what it implies for the celestial phenomena we currently take for granted. The mathematics of the future is simpler than the mathematics of the past, because we can reasonably assume that tidal dissipation rates will remain within a certain range. The continents will continue to drift, the ocean basins will continue to reconfigure, but the fundamental process will continue operating. The moon will continue to gain angular momentum from Earth's rotation. The days will continue to lengthen. The moon will continue to recede. Project forward 100 million years. This is a time span long enough for continents to travel thousands of kilometres, for new ocean basins to open and old ones to close, for evolution to produce creatures as different from us as we are from the dinosaurs. The moon will have retreated perhaps 4,000 to 5,000 kilometres, depending on the average recession rate over that interval. It will appear perhaps 1 to 2% smaller in the sky. Total eclipses will still occur, but they will be marginally shorter at maximum. The changes will be subtle. Project forward 200 million years. The moon will have retreated another 4,000 to 5,000 kilometres, now appearing perhaps 3 to 4% smaller than today. The maximum duration of totality will have decreased by perhaps 15 to 20 seconds. An eclipse chaser from this era, if such a thing could exist, might notice that eclipses seem briefer than the historical records suggest, but totality will still occur. Project forward 400 million years. Now we approach the transition zone. The moon will have retreated perhaps 15,000 to 20,000 kilometres from its current position. It will appear 5 to 7% smaller in the sky. Total solar eclipses will still occur, but only when the moon is near perigee and the sun is near apogee. The paths of totality will be narrower. The durations will be shorter. A growing fraction of central eclipses will be annular rather than total. And then, somewhere between 500 and 700 million years from now, depending on exact parameters that cannot be calculated with precision, the transition will complete. The last total eclipse will occur. The moon's angular diameter, even at its closest approach, will no longer exceed the sun's angular diameter, even at the sun's most distant point in its elliptical motion across Earth's sky. The geometry will have shifted past the critical threshold, and no configuration of positions will be able to restore what has been lost. The transition will not be abrupt from a cosmic perspective. It will stretch over millions of years, during which total eclipses become increasingly rare and increasingly brief. The last totalities will be measured in seconds rather than minutes, visible only along extremely narrow paths when orbital parameters align with extraordinary precision. And then the last of the lasts will occur, and then there will be no more. What follows will be an era of purely annular eclipses, when the moon passes directly in front of the sun but fails to cover it completely, leaving a ring of fire around the dark lunar disk. These annular eclipses will continue for billions of years, slowly evolving as the moon continues to recede, and the sun continues its own slow evolution toward red giant status. The ring of fire will grow wider, the silhouette of the moon shrinking against the solar disk, until eventually the moon's angular size becomes trivially small compared to the sun. But the loss of totality represents a specific, irreversible transition. The corona, visible only during totality, will become permanently hidden behind the glare of the uneclipsed sun. The diamond ring effect, the chromosphere, the prominences, the stars appearing at midday, the strange quality of light that totality creates, all of these will become impossible to see from Earth's surface without artificial intervention. the natural phenomenon that has inspired and terrified humanity since before recorded history will pass from the realm of possible experiences into the realm of memory and simulation. This is the knowledge that weighs upon anyone who truly understands lunar recession. The moon is leaving. The eclipses will end. The window is closing. And while the time remaining is vast beyond ordinary comprehension, it is also finite, bounded, running down with each passing year, each centimetre of recession, each millisecond added to the lengthening day. You stand at a moment in Earth's history when this particular wonder is still possible. Your ancestors stood at similar moments stretching back 4.5 billion years, though the eclipses they might have witnessed were different in character and duration. Your descendants, if they exist, will stand at moments when the wonder is fading, and eventually at moments when it has faded entirely. The long arc of the moon's departure creates a kind of cosmic urgency, a reminder that even the most seemingly permanent features of the natural world are temporary, contingent, passing. The tides continue to rise and fall. The moon continues to exert its gravitational influence. The energy continues to flow from Earth's rotation into the moon's orbit. And every second, imperceptibly but inexorably, the distance grows. The farewell continues. The Great Recession advances by another fraction of its annual increment. This is not tragedy in any human sense. The universe does not grieve for lost eclipses. Physics operates without sentiment or regret. The transfer of angular momentum is simply what happens when two massive bodies interact tidally, as inevitable as water flowing downhill, as implacable as entropy. But for conscious beings capable of appreciating the beauty of a totally eclipsed sun, capable of standing in the moon's shadow and feeling something like awe, the slow loss of this possibility carries a weight that mere physics cannot capture. The moon is your companion. It has been with you since before you were you, since before your species existed, since before life itself began. And it is slowly, gently, irrevocably saying goodbye. The handwriting is in the tidal rhythmites, in the ancient coral bands, in the laser reflections bouncing off the mirrors left by Apollo astronauts. The measurements agree, the predictions converge, the farewell is real. Yet the moon's slow departure is not merely a story of loss. It is also a story of what that departure reveals about the machinery of the cosmos, the hidden mechanisms that govern the dance of worlds, the intricate physics that transforms a simple gravitational attraction into a complex evolving system spanning billions of years. To truly understand why the moon recedes, to feel the inevitability of it rather than simply accepting it as astronomical fact, requires descending into the mathematics and mechanics that drive this ancient process. And there, in the equations and the physical principles, lies something unexpected. The same forces pushing the moon away are the forces that make Earth habitable. The same tidal interactions draining rotational energy are the interactions that have shaped the conditions under which life arose and flourished. The moon's departure is not incidental to Earth's story. It is woven into the very fabric of what makes this planet what it is. Consider the fundamental physics of tidal interaction. Two bodies orbiting their common centre of mass exert gravitational attraction on each other, and this attraction is not uniform. The near side of each body feels a stronger pull than the far side, simply because gravity weakens with distance according to the inverse square law. This differential pull creates a stretching effect, elongating each body slightly along the line connecting them. For Earth, this means the oceans bulge outward on both the side facing the moon and the side facing away, creating the familiar pattern of 2 high tides and 2 low tides each day. But this description, while accurate, misses the crucial detail that drives lunar recession. The bulge does not point directly at the moon. Earth rotates on its axis once every 24 hours, but the moon orbits Earth once every 27.3 days. This means Earth's rotation carries the tidal bulge ahead of the line connecting Earth and moon. The bulge leads the moon by a small angle, roughly 3 degrees, and this angular offset transforms the entire dynamics of the system. The mass concentrated in the leading tidal bulge exerts its own gravitational pull on the moon. Because the bulge is ahead of the moon in Earth's rotation, this pull has a component in the direction of the moon's orbital motion. It is as if an invisible hand were constantly giving the moon a gentle push, accelerating it ever so slightly in its orbit. And here is where orbital mechanics produces its counterintuitive result. An object accelerated in the direction of its orbital motion does not speed up. Instead, it climbs to a higher orbit, trading kinetic energy for gravitational potential energy. The Moon, pushed forward by Earth's tidal bulge, rises to a more distant orbit, and in doing so actually slows down, taking longer to complete each circuit around Earth. The acceleration makes the Moon move farther away and simultaneously makes it move more slowly. This is the engine of lunar recession. Earth's rotation, dragging the tidal bulge ahead of the Moon, creates a gravitational asymmetry that continuously transfers energy from Earth's spin to the Moon's orbit. The energy has to come from somewhere, and it comes from the only available reservoir, the rotational kinetic energy of Earth itself. Every joule added to the Moon's orbital energy is a joule subtracted from Earth's rotation. The planet spins down, the days lengthen, the Moon climbs away. The conservation laws are satisfied with perfect precision, energy and angular momentum flowing from one form to another, but never created or destroyed. The mathematics of this process were first worked out rigorously by George Darwin, the second son of Charles Darwin, who devoted much of his career to understanding the evolution of the Earth-Moon system. In the 1870s and 1880s, George Darwin developed a comprehensive theory of tidal friction and its effects on planetary rotation and satellite orbits. His calculations showed that the Moon must have been much closer to Earth in the distant past and would continue to recede in the distant future. He traced the implications of the physics across geological time, recognizing that the Earth-Moon system was not static but dynamically evolving, shaped by forces that operated imperceptibly on human timescales, but transformed the system utterly across the eons. Darwin's work built upon the foundation laid by Isaac Newton, who first understood the gravitational origin of tides, and upon the insights of Pierre-Simon Laplace and George Airy, who developed the mathematical theory of tidal dynamics in rotating systems. But Darwin pushed the analysis further than his predecessors, asking what the tidal forces implied about the history and future of the system. His answer was startling. The Moon, he calculated, might once have been close enough to Earth that the two bodies nearly touched, separated by a catastrophically small distance that would have produced tides of inconceivable violence. The energy dissipated by those ancient tides must have been enormous, slowing Earth's rotation from a few hours per day to the more leisurely 24-hour period we know today. Modern physics has refined Darwin's calculations, with improved understanding of tidal dissipation mechanisms and more accurate measurements of the current recession rate. The lunar laser ranging experiments, bouncing light off retroreflectors placed on the lunar surface by Apollo astronauts and unmanned Soviet missions, have measured the Earth-Moon distance with millimetre precision and confirmed the recession rate of 3.82 centimetres per year with extraordinary accuracy. This measurement, repeated thousands of times over decades, leaves no room for doubt about the basic phenomenon. The Moon is receding at almost exactly the rate predicted by tidal theory, given reasonable assumptions about the efficiency of tidal dissipation in Earth's oceans. But the simplicity of the basic mechanism conceals remarkable complexity in its details. Tidal dissipation does not occur uniformly throughout Earth's oceans. It is concentrated in specific locations where the geometry of ocean basins creates resonant amplification of tidal waves. The shallow seas on continental shelves, where the water column is compressed and tidal currents are forced through constricted passages, dissipate far more energy than the deep open oceans. The narrow gaps between continents, the long fjords and estuaries, the broad shallow basins, these are the friction points where Earth's rotational energy is converted into heat and transferred ultimately to the Moon's orbit. The current configuration of Earth's continents, with the Atlantic Ocean running north-south and the Pacific Ocean occupying nearly a hemisphere, happens to be particularly efficient at dissipating tidal energy. The tidal resonance of the North Atlantic in particular creates unusually large tides and unusually vigorous tidal currents, contributing disproportionately to the global energy dissipation. This means the current recession rate of 3.82 centimetres per year is not the long-term average but rather a geologically temporary peak. Throughout Earth's history, as continents drifted and ocean basins changed shape, the efficiency of tidal dissipation varied substantially. There were periods when the Moon receded faster than today, and periods when it receded much more slowly, depending on the accidents of continental geometry and the resonant properties of the resulting ocean basins. This variation complicates the extrapolation of lunar history from current measurements. If the moon has always receded at 382 centimetres per year, simple arithmetic suggests it would have been touching Earth only 1.4 billion years ago. But Earth is 4.5 billion years old, and the geological and geochemical evidence indicates the moon has been present at significant distance for nearly all of that time. The discrepancy resolves when you account for the changing efficiency of tidal dissipation. In the past, when ocean basins had different shapes and continental configurations were different, the average recession rate was slower, perhaps 1 or 2 centimetres per year rather than nearly 4. The moon's journey from its primordial proximity to its current distance took longer than a constant recession rate would suggest. The physics of the situation also involves a subtle feedback mechanism that stabilizes the recession process against runaway acceleration. As the moon moves farther from Earth, the tidal forces it produces become weaker, scaling with the inverse cube of the distance. Weaker tidal forces mean less distortion of Earth's oceans, less energy dissipated in tidal friction, and slower recession. The process is self-limiting in a sense. The farther the moon retreats, the gentler its gravitational influence becomes, and the more slowly it continues to retreat. This is why the moon's departure, though inexorable, will stretch across billions of years rather than concluding in mere millions. The very forces that drive the recession also moderate its pace, creating a long, drawn-out farewell rather than a sudden departure. The destination of this process, if it were allowed to run to completion uninterrupted, would be a state physicists call tidal locking. Eventually, after tens of billions of years, Earth's rotation would slow to the point where its day equals the moon's orbital period. The tidal bulge would no longer lead or lag the Earth-Moon line. The gravitational asymmetry driving the recession would vanish, and the moon would settle into a stable final orbit, neither approaching nor receding, perpetually fixed at the same point in Earth's sky. This final state, a mutual tidal lock where each body keeps the same face toward the other, has already been achieved by the moon itself. The far side of the moon, never seen from Earth until spacecraft photographed it, remains hidden because the moon long ago surrendered its rotation to tidal forces, slowing its spin until it rotates exactly once per orbit. Earth is on the same path but has much further to go. The timeline for reaching this final state is so long that it becomes essentially meaningless. Current calculations suggest Earth's day would need to increase from 24 hours to roughly 47 days before the mutual lock is achieved. At current recession rates, this would take more than 50 billion years, but the Sun will exhaust its hydrogen fuel and enter its red giant phase in approximately 5 billion years, expanding to engulf, or at least dramatically affect the inner planets, including Earth. The long-term fate of the Earth-Moon system is thus not tidal locking but solar destruction. The Moon's patient departure will be interrupted by the death of the Sun, the farewell cut short by a more dramatic cosmic event. But these ultimate fates are so distant that they serve mainly to provide context, to place the Moon's recession within the larger narrative of stellar and planetary evolution. The more immediate implications, immediate on a geological timescale, are the ones that matter for understanding the significance of the process. And here the physics reveals something profound. The tidal forces that drive lunar recession are not merely moving the Moon away, they are fundamentally shaping the conditions under which life evolved on Earth. Consider the length of the day. 4.5 billion years ago, when the Moon was newly formed and orbiting perhaps 15,000 kilometres from Earth rather than the current 384 to 400, Earth spun on its axis in roughly 6 hours. The tides raised by such a close moon were monstrous, not the gentle rise and fall of a few metres that we know today, but vertical movements of water perhaps hundreds of metres high. The energy dissipation was correspondingly enormous, and Earth's rotation slowed rapidly. By the time the first complex life appeared in the Cambrian explosion, roughly 540 million years ago, the day had lengthened to approximately 21 hours. The coral growth rings and tidal rhythmites from this era confirm this calculation independently. Life evolved in a world where days were significantly shorter than today, where the sun rose and set more frequently, where the basic rhythm of existence was compressed into a faster cycle. The gradual lengthening of the day may have had subtle but significant effects on the evolution of biological rhythms. Circadian clocks, the internal timekeeping mechanisms that regulate sleep and wakefulness, hormone release, and countless other physiological processes are calibrated to the day-night cycle. These clocks evolved over hundreds of millions of years as the day itself was slowly lengthening. The organisms we see today, including ourselves, carry within our cells the accumulated adaptation to a progressively slowing planetary rotation. Whether this slow change influenced the architecture of biological timekeeping in any fundamental way remains an open question, but the possibility is tantalizing. The moon's recession, by lengthening Earth's day, may have left its mark on the very machinery of life. More certain is the effect of the moon's departure on Earth's axial tilt. Earth's rotation axis is currently tilted at approximately 23.5 degrees relative to the plane of its orbit around the Sun. This tilt is responsible for the seasons, creating the variation in day length and solar intensity that drives the annual cycle of weather patterns, biological rhythms, and ecological dynamics. The tilt is not fixed. It varies over time under the gravitational influence of the Sun and other planets, oscillating between roughly 22.1 and 24.5 degrees over a cycle of approximately 41,000 years. These Milankovitch cycles, named after the Serbian mathematician who first calculated their effects, contribute to the Ice Age cycles that have shaped Earth's climate over the past few million years. But Earth's axial tilt is remarkably stable, compared to what it would be without the Moon. Mars, which has no large moon, experiences chaotic variations in its axial tilt, swinging between 0 and 60 degrees over millions of years. These wild oscillations produce correspondingly extreme climate variations, contributing to the loss of surface water and atmospheric erosion that have made Mars the cold, dry world we see today. Earth's moon, by exerting a gravitational influence that dampens these oscillations, stabilizes our planet's axial tilt within a relatively narrow range. This stability may have been crucial for the development and persistence of complex life. A planet whose tilt swings wildly from nearly vertical to nearly horizontal would experience climate extremes that might prevent the long-term stability ecosystems require to evolve. As the moon recedes, its stabilizing influence weakens. At greater distances, the lunar gravitational force that keeps Earth's tilt in check becomes less effective. Models suggest that once the moon reaches a certain distance, roughly several 100,000 kilometers beyond its current position, its stabilizing effect will diminish significantly. Earth's axial tilt may then begin to vary more dramatically, potentially destabilizing the climate patterns that have characterized our planet for the past several 100 million years. This is not a near-term concern. The timescale for such changes is hundreds of millions to billions of years, but it represents another consequence of the moon's slow departure, another way in which the recession reshapes the conditions of habitability. The tides themselves, beyond their role in transferring energy from Earth's rotation to the moon's orbit, have played a significant part in the history of life. The intertidal zone, that strip of coastline alternately submerged and exposed as the tides rise and fall, is one of the most biologically productive and evolutionary dynamic environments on Earth. The rhythmic flooding and draining of tidal flats creates conditions that may have been crucial for the transition of life from ocean to land. Organisms in the intertidal zone experience twice-daily cycles of submersion and exposure, developing adaptations for surviving in both aqueous and aerial environments. Some theories of the origin of terrestrial life suggest that this tidal zone served as a proving ground, selecting for the physiological innovations that eventually allowed life to colonize the continents. As the moon recedes and the tides become weaker, this dynamic environment will gradually calm. The difference between high and low tide will diminish. The intertidal zone will shrink. The twice-daily pulse of marine influence reaching across the shoreline will become a gentler rhythm, the waves still breaking but the vertical range of the tides reduced. This change will take hundreds of millions of years to become significant, but its direction is set. The tidal environment that may have helped launch life onto land will slowly fade, a casualty of the same physics that drives the moon away. All of this, the lengthening days, the stabilized axial tilt, the evolving tides, represents the deep entanglement of Earth's habitability with the presence and proximity of the moon. The recession is not merely moving a bright object in the sky farther away. It is slowly unwinding the conditions that have made Earth the particular kind of planet it is. The moon's gravitational influence, so central to the character of our world, diminishes with each passing year, each centimetre of increased distance. The planet that emerges on the far side of this process, hundreds of millions and billions of years hence, will be a different Earth, one where the days are longer, the tides are weaker, and the stabilizing influence of the lunar companion has faded to insignificance. The physics ensures this outcome. The equations are relentless, the conservation laws absolute. Angular momentum flows from Earth's spin to the Moon's orbit, and no force in the solar system can reverse that flow as long as Earth rotates faster than the Moon orbits. The dissipation continues, measured in terawatts of power, the equivalent of thousands of nuclear power plants, all extracted from the planet's rotation and converted to heat in the shallow seas, and ultimately to the gravitational potential energy of the Moon's higher orbit. The engine runs day and night, tide after tide, millennium after millennium, and will continue running for as long as Earth remains intact. This is the mechanism behind the farewell. Not sentiment, not tragedy, not cosmic intention, but physics operating with the same indifference it brings to every process in the universe. Masses interact, energy flows, systems evolve towards states of lower energy dissipation. The Earth-Moon system is no exception, subject to the same laws that govern the spiralling of galaxies and the cooling of stars. The Moon's recession is simply what happens when a planet with oceans hosts a large natural satellite. It is as natural as gravity itself, as unremarkable from a cosmic perspective as a rock rolling downhill. And yet, for beings who have looked up at the Moon and wondered, who have watched eclipses and felt awe, who have measured the centimetres and understood the implications, the physics carries a weight that transcends its equations. To know that the Moon is receding is to know that time passes in ways deeper than the human scale, that the universe evolves on timescales that dwarf not just individual lives, but entire civilizations, entire species, entire geological eras. It is to stand at one moment in a story that began before you and will continue after you, a story written in the language of angular momentum and tidal dissipation and gravitational potential energy. The numbers are precise, the mechanisms are understood, the predictions are robust, and the farewell continues, centimetre by centimetre, year after year, pulling the Moon along a trajectory set in motion when the solar system was young and the Moon was born in fire. But here is where the story transforms from elegy to something stranger, something that carries within it the architecture of hope. Because the physics that seems to write only departure, only loss, only the gradual unwinding of everything we have known, contains within its very equations a destination. The Moon is not simply leaving. It is travelling toward a specific endpoint, a configuration where the farewell will finally cease, where Earth and Moon will reach a state of equilibrium that the mathematics has been pointing toward for 4.5 billion years. This equilibrium has a name. Astronomers call it tidal locking, and it represents one of the most profound endpoints in gravitational physics. We have already seen one half of this phenomenon. The Moon shows us the same face eternally, because Earth's tidal influence on the Moon completed its work long ago, slowing the Moon's rotation until it matched its orbital period, until the Moon's day became exactly as long as its month. The Moon is already tidally locked to Earth, trapped in a gravitational embrace that keeps its familiar near side perpetually facing us, its mysterious far side turned eternally away. But tidal locking can work both ways. Just as the Moon has been locked to Earth, Earth is slowly, inexorably being locked to the Moon. The same tidal forces that pull the Moon outward are pulling Earth's rotation downward, slowing the planet's spin until eventually, impossibly far in the future, Earth's day will match the Moon's orbital period. When that happens, the tidal friction will cease. The angular momentum transfer will halt. The Moon's outward spiral will stop, and for the first time since the solar system formed, the Earth-Moon system will reach a state of gravitational rest. The mathematics describing this final state emerge from the work of 19th century astronomers who extended the tidal calculations forward and realized that the current configuration is not the destination, but merely a way station. George Darwin, son of Charles Darwin and himself a distinguished mathematician, worked out many of the details in the 1870s and 1880s. His calculations showed that the tidal interaction contains an endpoint, a final state, where Earth and Moon rotate as if rigidly connected, both bodies perpetually facing each other across a gap much larger than the current distance. The numbers describing this final configuration are staggering. When tidal locking is complete, Earth's day will be approximately 47 of our current days long. The sun will rise and crawl across the sky with glacial slowness, taking nearly 24 days to reach noon, then another 24 days to set. The moon's orbital period will match this stretched day, meaning the moon will hover almost motionlessly in the sky for observers on the hemisphere facing it, while remaining forever invisible from the opposite hemisphere. The moon's distance at this point will be approximately 550,000 kilometres, roughly 40% farther than its current distance, though estimates vary somewhat depending on model parameters. This is the equilibrium toward which every centimetre of recession points. Every tide that sloshes across the continental shelves, every microscopic heating of rock and water by tidal friction, every year's increment of 3.8 centimetres constitutes progress toward this final state. The physics is not simply dissolving the Earth-Moon relationship, it is evolving the relationship toward its lowest energy configuration, the state from which no further evolution is possible through tidal means alone. Understanding why this equilibrium ends the recession requires grasping a subtle point about tidal physics. The energy transfer that drives the moon outward occurs because Earth rotates faster than the moon orbits. This speed differential creates a tidal bulge that is dragged slightly ahead of the moon's position, and this bulge pulls the moon forward in its orbit, speeding it up and raising it to a higher altitude. But if Earth's rotation rate were to slow until it matched the moon's orbital period exactly, this differential would vanish. The tidal bulge would align directly with the moon's position, pointing neither ahead nor behind. No forward pull, no acceleration, no outward migration. The system would be frozen in gravitational equilibrium, neither advancing nor retreating. The moon itself demonstrates this principle. Early in lunar history, the moon rotated independently, showing different faces to Earth at different times. But Earth's tidal influence on the moon, vastly stronger than the moon's influence on Earth given the mass ratio, slowed the moon's rotation relatively quickly on geological timescales. Within perhaps 100 million years of the moon's formation, its rotation had synchronized with its orbit. The tidal bulge Earth raises on the moon now points directly at Earth at all times, neither ahead nor behind. No angular momentum transfers, no orbital evolution from this source. The moon's tidal locking to Earth is complete, and has been complete for over 4 billion years. Earth's journey toward the same state will take vastly longer. The moon's tidal effect on Earth is much weaker than Earth's tidal effect on the moon, proportional to the cube of the mass ratio, and inversely proportional to the cube of the distance. Earth's rotation is slowing by only milliseconds per century, a rate that seems negligible against the backdrop of a 24-hour day, but that accumulates inexorably over deep time. The endpoint exists, guaranteed by the mathematics, but reaching it requires patience measured in epochs. How long will this journey take? The estimates vary because the calculation depends sensitively on future configurations of Earth's continents and oceans, on the depth and geometry of shallow seas where tidal dissipation occurs most efficiently, on factors that cannot be predicted billions of years in advance. But the order of magnitude is clear. Complete mutual tidal locking of Earth and Moon will require somewhere between 50 billion and 100 billion years. Write those numbers slowly. 50 to 100 billion years. The current age of the universe is approximately 13.8 billion years. The Sun will exhaust its hydrogen fuel and expand into a red giant in roughly 5 billion years, engulfing the inner planets and quite possibly Earth itself. The Milky Way will collide with the Andromeda Galaxy in approximately 4.5 billion years, scattering stars across the merged remnant. These events will occur long before the Earth-Moon system reaches tidal equilibrium. This is the profound twist in the mathematics of lunar recession. The physics points toward an equilibrium, writes the equations of a final state with perfect precision, calculates the configuration where the farewell will cease. But the timeline of that journey extends far beyond the timeline of the Earth-Moon system's existence. The endpoint is unreachable, not because the physics fails, but because the universe will intervene, because the Sun will die, because the very stage on which this gravitational drama unfolds will be dismantled before the final act can play. The Moon is travelling toward a destination it will never reach. This creates a peculiar kind of tragedy, different from simple departure. The farewell is not eternal in the sense of continuing forever, because nothing in the universe continues forever. But it is eternal in the sense that matters, the sense that maps onto the existence of the system itself. For as long as there is an Earth and a Moon, for as long as these two bodies maintain their relationship, the recession will continue. The equilibrium will remain forever approaching, forever out of reach, like a mathematical asymptote that the system approaches but cannot touch within the time allotted. The numbers illuminate the phases of this incomplete journey. In 600 million years, when the last total solar eclipse fades into history, the Moon will have receded approximately 23,000 additional kilometres, reaching a distance of roughly 407,000 kilometres. Earth's day will have lengthened by perhaps 2 hours, stretching toward 26 hours. The tidal dissipation will continue, somewhat reduced as the Moon's gravitational influence weakens with distance, but still substantial, still measured in terawatts. In 1 billion years, the Moon will hover approximately 420,000 kilometres distant. Earth's day will approach 28 hours. The Sun will have brightened enough to raise Earth's surface temperature significantly, potentially triggering runaway greenhouse effects that end the era of liquid surface water. Whether tides still slosh across shrinking seas or have evaporated entirely will depend on the details of climate evolution that no current model can predict. But the physics of recession will continue regardless of surface conditions, driven by the solid Earth tides that continue even in a waterless world, though at a much slower rate. In 3 billion years, the Moon will reach approximately 450,000 kilometres, though by this point the predictions become increasingly uncertain. Earth's day will have stretched toward 35 hours or more. The Sun will be growing unstable, beginning the transition that will ultimately swell it into a red giant. The Moon's recession rate will have slowed significantly, its weakening gravitational grasp raising smaller tidal bulges, extracting less angular momentum with each diminished flexing of the planet. But the direction will remain the same. Outward, always outward. And then, approximately 5 billion years from now, the Sun will exhaust the hydrogen fuel in its core and begin the expansion that defines stellar death for stars of its mass. The outer layers will swell, engulfing Mercury and Venus certainly, quite possibly reaching Earth's current orbit. What happens to the Earth-Moon system in this convulsion remains uncertain, subject to details of mass loss and gravitational dynamics that depend on models still being refined. The Earth may be engulfed by the expanding Sun, vaporized in plasma hotter than any substance can withstand. The Moon may survive slightly longer given its greater distance, or may be dragged inward as the Sun's mass loss alters the gravitational balance, or may escape to orbit the white dwarf remnant that will remain after the Sun sheds its outer layers. What will not happen is the completion of tidal locking. The 47-day equilibrium, the gravitational rest state toward which every centimetre of recession has pointed, will remain forever unreached. The Moon's journey will end not in arrival, but in interruption, the destination visible in the mathematics, but blocked by the mortality of stars. This incompleteness resonates with something deep in the human experience of time. We are accustomed to processes that reach conclusions, stories that have endings, journeys that arrive at destinations. The narrative arc of beginning, middle and end shapes how we understand events at every scale. But the Earth-Moon system defies this expectation. Its story has a beginning, written in the fires of the moon-forming impact. Its story has a middle, the billions of years of recession we are living through. But its story has no proper ending, only an interruption that will prevent the final state from ever being realized. There is a strange comfort in this incompleteness, if you allow yourself to feel it. The Moon is not simply leaving. It is travelling towards something, even if that something lies beyond the system's lifetime. The physics contains purpose, even if that purpose cannot be fulfilled. Every centimetre of recession represents progress, however incremental, however ultimately frustrated, toward a state of equilibrium that the mathematics defines with perfect clarity. The journey has a direction. The direction has a destination. That the destination is unreachable does not erase its existence from the equations. Consider what this means for the present moment, for the act of standing beneath the current moon and watching it traverse the current sky. You are witnessing a system in motion, not randomly, but directionally, travelling a trajectory set by the laws of physics toward an endpoint specified by those same laws. The Moon hangs in the sky tonight approximately 384,400 kilometres distant, give or take depending on where it sits in its elliptical orbit. It is 23,000 kilometres closer than it will be when total solar eclipses become impossible. It is roughly 165,000 kilometres closer than it will be when the Sun begins its death throes. It is approximately 165,000 kilometres closer than the equilibrium distance that physics describes, but time forbids. You are standing at one point along a trajectory billions of years long, a trajectory that began when the solar system was young and will end when the sun dies. The moon you see tonight is neither the moon of the deep past, closer and larger and faster in its orbit, nor the moon of the deep future, farther and smaller and slower. It is the moon of this precise moment, occupying its precise position on a journey that spans the entire lifetime of the solar system. The equations governing this journey are among the most thoroughly tested in all of physics. Tidal theory, developed by George Darwin and refined by generations of geophysicists, describes the energy transfer with remarkable precision. Radar ranging to the lunar retroreflectors confirms the recession rate to within fractions of a millimetre. Geological evidence from tidal rhythmites spanning hundreds of millions of years validates the predictions backward through deep time. The physics is not speculation or approximation. It is measurement confirmed by independent methods, prediction verified by observation, mathematics validated by the behaviour of the actual system. This scientific certainty carries its own form of meaning. The lunar recession is not a mystery requiring faith to accept. It is not an interpretation subject to revision. It is not a theory awaiting the discovery that might overturn it. The moon is receding by 3.8 centimetres per year because angular momentum is conserved and tidal friction is real, and energy must go somewhere. These are not beliefs but measurements. These are not opinions but physics. And the physics reveals something remarkable about equilibrium and time. The final state of tidal locking is not merely a theoretical construct, but a genuine destination encoded in the current behaviour of the system. Every tide that rises and falls today is a tide that converts Earth's rotational energy into lunar orbital energy, a tide that moves the system infinitesimally closer to the equilibrium state. The destination shapes the journey, even though the journey will never arrive. The equilibrium is present in every moment of the recession, implicit in the direction of the energy flow, visible in the mathematics even when invisible in the sky. This is the profound lesson embedded in the physics of tidal locking. Unreachable destinations still organise the behaviour of systems travelling toward them. The equilibrium the moon will never reach still determines the direction of its motion. The 47-day final state that will never be realised still pulls the present toward it, still defines which way is forward, still gives meaning to the concept of progress even in the absence of arrival. The journey matters even when the destination is impossible. There is a cosmological echo of this principle that extends far beyond the Earth-Moon system. Throughout the universe, systems evolve toward equilibrium states they may never reach. Stars burn toward configurations interrupted by supernova explosions. Galaxies merge toward gravitational balance disrupted by dark energy's acceleration. Black holes evaporate toward quantum completeness on timescales that exceed the lifetime of the cosmos itself. The universe is full of journeys toward unreachable destinations, processes aimed at endpoints that intervening events will prevent. The Earth-Moon system belongs to this cosmic category. Its incomplete journey toward tidal locking places it in the company of countless other systems throughout the universe, all evolving according to physics that defines equilibrium states, all interrupted by the finite lifetimes of the structures performing this evolution. There is no tragedy in this pattern, or if there is, the tragedy is so universal that it ceases to feel tragic, becoming instead simply the way things are, the texture of a universe where time moves only forward and nothing lasts forever. The moon tonight hangs in the sky as it has hung for billions of years, a familiar presence that seems eternal precisely because human timescales cannot perceive its motion. But the motion is there, written in the equations, confirmed by the measurements, visible in the retroreflector data accumulating year after year, 3.8 centimetres, the width of a golf ball, the thickness of a small book. Nothing you could see, nothing you could feel, nothing that registers against the vast distance already separating Earth from Moon. And yet this increment, multiplied by the years, multiplied by the millions and billions of years that constitute deep time, builds towards something, not the equilibrium itself which lies beyond the system's lifetime, but the approach to equilibrium, the journey toward the unreachable destination, the process of becoming something different from what was. The moon is not simply departing, it is evolving toward a state, incomplete as that evolution must remain. This evolution will transform what future observers see when they look at the sky. In 600 million years, if complex life still exists to observe, the Moon will appear noticeably smaller, its angular diameter reduced by roughly 6% from current values. The difference may seem subtle, but it is the difference between a Moon that can cover the Sun and a Moon that cannot. The difference between total solar eclipses and their permanent absence. The observers of that distant era will know about total eclipses only through records and reconstructions. The way we know about dinosaurs or the formation of continents. The phenomenon will have passed from experience into history, another casualty of the journey toward unreachable equilibrium. The approach to equilibrium also shapes the Earth itself in ways beyond the simple slowing of rotation. As Earth's day lengthens, atmospheric and oceanic circulation patterns must adjust. Weather systems powered partly by the Coriolis effect will redistribute themselves as that effect weakens. Ocean currents driven by the interplay of rotation and solar heating will evolve toward new configurations. These changes will unfold over hundreds of millions of years, imperceptibly slow but cumulatively significant, reshaping the planetary environment in ways that the physics of tidal locking sets in motion but does not determine in detail. The equilibrium serves as a strange kind of attractor, shaping behaviour without being reached, influencing the present from a future that will never arrive. This is not mysticism but mathematics, the way that the direction of energy flow organises the behaviour of physical systems. Water flows downhill toward the sea even if the stream dries up before reaching it. Heat flows from hot to cold even if the system reaches room temperature before true equilibrium. Angular momentum flows from Earth's spin to lunar orbit even if the Sun explodes before the transfer is complete. The direction matters even when the destination is unreachable. Standing beneath the Moon tonight, you stand at one moment in this directional flow. The moment is unremarkable in the sense that every moment for the past 4 billion years has been equally unremarkable, equally poised between a closer past and a farther future. But the moment is also privileged in the sense that you are aware of it, that you understand what the centimetres mean, that you can hold in your mind both the physics and the implications. The Moon recedes whether or not anyone knows it is receding. But knowing it is receding changes what it means to see the Moon, transforms the familiar presence into something dynamic, something temporary, something participating in a journey that spans the lifetime of worlds. The equilibrium toward which the Moon travels exists in the mathematics with perfect clarity. The 47-day mutual tidal lock, the 550,000 kilometre separation, the eternal facing of the same hemispheres across the gap of space. This state is real in the sense that all mathematical truths are real, derivable from first principles, calculable to any desired precision. It simply will never be physically realised, not because the mathematics is wrong, but because the universe is mortal, because stars die, because time runs out before physics completes its work. The Moon is travelling toward a destination it will never reach. This is not a metaphor for human striving, though it echoes such metaphors with uncanny precision. It is simply the truth about a physical system, stated without sentiment or interpretation. The physics defines a goal. The chronology prevents its achievement. The system continues anyway, centimetre by centimetre, year by year, tide by tide, progressing toward what can never be attained. And somewhere in this impossibility lies the deepest meaning of lunar recession. Not the departure itself, though departure is real. Not the loss of eclipses, though that loss will come. Not the transformation of Earth, though transformation continues. But the structure of the journey, the directional flow toward unreachable equilibrium, the way that physics organises motion toward destinations that existence itself makes impossible. The Moon embodies this structure, makes it visible, makes it personal in a way that abstract physics cannot. Every time you look up at the Moon, you see a body in transit, travelling a trajectory billions of years long toward an endpoint 50 billion years away, an endpoint it will miss by 45 billion years or more because the Sun will die first. The numbers are precise, the physics is certain, the equilibrium is unreachable, and the journey continues, written in every tide, measured in every laser pulse, accumulated in every centimetre of recession, pointing forever toward a destination that forever recedes, not through space, but through the mortality of everything that exists. But physics does not only point toward unreachable futures. It also offers tools, methods for grasping what we cannot directly experience, techniques for making the invisible visible and the imperceptible measurable. The story of lunar recession is therefore also a story of human ingenuity, of the remarkable instruments and observations that transform 3.8 centimetres per year from an abstraction into a measured fact, from a theoretical prediction into a verified physical reality. The moon's departure is certain not because equations say so, but because we have watched it happen year after year, decade after decade, with precision that borders on the miraculous. The primary tool for this measurement carries a name that sounds almost too simple for what it accomplishes: lunar laser ranging. The principle is elementary, the kind of experiment a child could design. You shine a light at the moon, wait for it to bounce back, measure how long the round trip takes, and calculate the distance from the travel time. Light moves at a known speed. Time can be measured with extraordinary precision. Distance follows from these two facts with mathematical certainty, but the execution of this simple principle required solving problems that initially seemed insurmountable. A laser beam, no matter how tightly focused, spreads as it travels. Over the 384,000 kilometres to the moon, even the most precisely collimated beam expands to cover several kilometres of lunar surface. The light that returns is fainter still, scattered across the entire journey back, arriving at Earth as the palest whisper of the original pulse. A laser that leaves Earth carrying perhaps a billion photons returns with only a handful, sometimes a single photon, sometimes none at all. Detecting these sparse returns against the noise of moonlight, starlight, and atmospheric scattering required detectors of extraordinary sensitivity and timing systems capable of measuring intervals shorter than a billionth of a second. The solution to the return signal problem came not from better detectors alone, but from the Apollo missions. On July 23, 1969, just hours after Neil Armstrong spoke his famous words, Buzz Aldrin deployed a device called a retroreflector array on the lunar surface. The array consisted of 100 fused silica corner cubes, each a prism-like structure designed with a remarkable property. Light entering the cube reflects from 3 perpendicular surfaces and exits travelling exactly parallel to its incoming direction, regardless of the angle at which it arrived. Aim a laser at a corner cube from any orientation, and the return beam travels straight back to its source. This property transforms the measurement problem entirely. Instead of scattering across kilometres of lunar regolith, the laser light that strikes the retroreflector returns in a tight cone aimed precisely at Earth. The enhancement factor is enormous. A corner cube array roughly the size of a suitcase returns a signal millions of times stronger than the same area of ordinary lunar surface would produce. Still faint by any human standard, still requiring heroic effort to detect, but suddenly feasible rather than impossible. The Apollo 11 retroreflector was only the first. Apollo 14 carried another array, deployed by Alan Shepard in February 1971. Apollo 15, arriving in July of the same year, brought the largest array, 3 times the size of its predecessors, containing 300 corner cubes arranged in a panel roughly the size of a small tabletop. The Soviet Union contributed as well, landing unmanned rovers carrying French-built retroreflectors in 1970 and 1973. The Lunokhod 1 reflector, lost for decades when contact with the rover was lost, was rediscovered in 2010 and began returning signals once more, a ghost instrument resurrected by careful searching. 5 retroreflectors now dot the lunar surface, an array of targets enabling measurements from multiple locations on both Earth and Moon. The first successful ranging experiment occurred on August 1, 1969, just days after Armstrong and Aldrin returned to Earth. A team at Lick Observatory in California fired a ruby laser through the facility's 120-inch telescope and detected returning photons roughly 2.5 seconds later. That initial measurement achieved an accuracy of perhaps 25 centimetres, remarkable for a first attempt but crude by modern standards. The Moon's distance could now be measured better than ever before in human history, but the precision needed to detect 3.8 centimetres of annual recession was still beyond reach. 50 years of refinement changed everything. The lasers grew more powerful and more precisely timed. The detectors became capable of registering single photons and time-stamping their arrivals to picosecond precision. The atmospheric modelling improved, allowing corrections for the way air bends and delays light depending on temperature, pressure, and humidity. The data analysis techniques evolved, combining millions of individual ranging observations to extract distance measurements of almost incomprehensible accuracy. The Apache Point Observatory Lunar Laser Ranging Operation, known by its acronym APOLLO, represents the current pinnacle of this half-century refinement. Located in the Sacramento Mountains of New Mexico at an altitude of 2,800 meters, the facility fires a green laser through a 3.5-meter telescope, delivering pulses roughly 100 trillionths of a second long. Each pulse contains roughly 3 billion photons. Roughly 1 photon in 30 billion completes the round trip and triggers the detector. The system fires 20 pulses per second, accumulating enough returns over an observing session to determine the Moon's distance to an accuracy of approximately 1 millimeter. 1 millimeter. The thickness of a paperclip wire. The width of a pencil mark. This is the precision with which we now measure the distance to a body 384,000 kilometers away. A precision of roughly 3 parts in a trillion. If the distance from New York to Los Angeles could be measured with comparable accuracy, the uncertainty would be smaller than the diameter of a human hair. At this level of precision, the Moon's annual recession of 3.8 centimeters stands out like a beacon. Over a single year, the measurement uncertainty is roughly 1 millimeter, while the recession is roughly 38 millimeters. The signal exceeds the noise by a factor of nearly 40. Over a decade, the accumulated recession of 38 centimeters becomes unmistakable. Over the 50-plus years since the first Apollo measurements, the Moon has receded by more than 2 meters, a change that the laser ranging data capture with perfect clarity. The measurements do more than confirm the recession rate. They reveal its structure, its variations, its complex dependencies on factors that simpler theories might overlook. The Moon does not recede at a perfectly constant rate, but varies subtly from year to year, influenced by factors including the distribution of water in Earth's oceans, the changing shape of the ocean basins, and the complex internal structure of the mantle through which tidal flexing propagates. The data show tiny oscillations superimposed on the steady trend, wiggles that encode information about processes deep within the Earth that would otherwise remain hidden. More remarkably still, the ranging data have tested Einstein's general theory of relativity with extraordinary precision. The Moon's orbit follows curved space-time geometry, and the millimeter-level measurements are sensitive enough to detect relativistic effects that Newton's theory cannot predict. The data confirm that Einstein's equations describe lunar motion with an accuracy of better than 1 part in 10 trillion, making the Earth-Moon system one of the most precise laboratories for gravitational physics anywhere in the universe. The same measurements that track the Moon's departure also validate the fundamental theory of gravity that explains why it departs. The retroreflectors themselves present a gradually accumulating puzzle. Over the decades since their deployment, the return signals have weakened significantly. The Apollo 15 array, once the strongest source, now returns roughly 10 times fewer photons than it did in the early 1970s. The leading explanation involves lunar dust, electrostatically levitated by ultraviolet light and gradually coating the reflector surfaces. The degradation continues, the signals growing fainter year by year, a kind of slow blindness overtaking the instruments. New reflectors would help, and several nations have plans to deploy them. India's Chandrayaan-3 mission in 2023 carried a small retroreflector array, contributing a new target to the network. NASA's Artemis program includes provisions for additional retroreflectors on future lunar landing missions. Each new reflector extends the capabilities of the global ranging network, enabling measurements from new locations and providing backup against the continued degradation of the original Apollo instruments. But laser ranging is not the only tool in the measurement arsenal. Radio telescopes have contributed their own constraints on lunar motion, tracking spacecraft in lunar orbit with precision that complements the retroreflector data. The Gravity Recovery and Interior Laboratory mission, known as GRAIL, placed twin spacecraft in lunar orbit and measured their separation with microwave ranging accurate to better than a micrometer. While GRAIL's primary mission was mapping the Moon's internal mass distribution, the orbital data it collected added new constraints on lunar recession, confirming the laser ranging results through an entirely independent technique. Satellite laser ranging, the extension of lunar ranging principles to artificial satellites orbiting Earth, has contributed indirectly by improving our understanding of Earth's gravitational field and rotation. The LEGIOS satellites, launched in 1976 and 1992, are essentially giant retroreflectors in Earth orbit, dense spheres covered with corner cubes that enable ranging with millimetre precision. The data from these satellites help calibrate the terrestrial reference frames against which lunar ranging measurements are made, reducing systematic errors and improving the overall accuracy of the distance determination. The measurement campaign represents one of the longest-running precision experiments in the history of science. For more than half a century, observatories around the world have fired lasers at the moon and timed the returns, accumulating a dataset that now spans 2 full human generations. The scientists who began this work in 1969 have retired or died. Their students have retired in turn. The third generation of researchers now continues the observations, inheriting not just the equipment and the techniques, but the unbroken thread of data stretching back to the first Apollo retroreflector deployment. This continuity matters because detecting slow change requires long baselines. A recession rate of 3.8 centimetres per year is undetectable over a single observation, marginal over a single year, clear over a decade, and overwhelming over 50 years. The patient accumulation of data transforms what would be imperceptible noise into unmistakable signal. Science often rewards the persistent, those willing to continue measurements long after the initial excitement fades, long after the funding agencies grow restless, long after the next shiny mission captures public attention. Lunar ranging exemplifies this persistence, the quiet heroism of sustained measurement. The ranging data have also provided unexpected dividends, discoveries that the original experimenters could not have anticipated. The measurements are sensitive enough to detect the gravitational effects of large earthquakes, which redistribute mass within Earth and subtly alter the planet's rotation. They can observe the annual cycle of water moving between oceans and continents, the glaciers growing and melting, the monsoons arriving and departing. They have constrained the possibility that the gravitational constant might be changing over time, a question that general relativity answers with a firm negative, but that certain alternative theories leave open. Every improvement in ranging precision opens new windows onto physics that cruder measurements could not access. The broader lesson extends beyond the specific case of lunar recession. We live in an era of unprecedented measurement capability, able to detect changes that would have been utterly invisible to all previous generations. The universe operates on scales of time and distance that human senses cannot directly perceive, but human instruments can now reach those scales, can measure the millimeters that accumulate into the cosmic drift of worlds. This capability transforms our relationship with phenomena that once seemed eternal and unchanging into an understanding of continuous measurable transformation. Consider what the ranging measurements tell us about the recent history of the Moon's recession. The 3.8 centimetres per year observed today is not the rate that has prevailed throughout Earth's history. Geological evidence from ancient tidal deposits suggests that the recession rate has varied significantly over time, faster when the continents were arranged to maximise tidal dissipation, slower when the oceanic geography was less favourable to energy loss. The current rate appears to be anomalously high by geological standards, possibly related to the specific configuration of today's ocean basins and continental shelves. Reconstructing the full history requires combining the precision-ranging data of the present with the broader but less precise geological constraints of the deep past. Tidal rhythmites, the layered sedimentary deposits that record ancient tidal cycles, provide snapshots of Earth's rotation rate at various times in the past. These snapshots can be converted into estimates of lunar distance through the physics of angular momentum conservation. The work is painstaking, requiring careful identification of suitable rock formations, meticulous counting of layers, and sophisticated analysis to extract the tidal signal from the geological noise. One particularly valuable archive exists in the Wheelie Volley Formation of Western Australia, a sequence of banded iron formations approximately 2.46 billion years old. The layers show a clear modulation that researchers have interpreted as a tidal signal, encoding information about the Earth-Moon system when the planet was barely half its current age. Analysis of these layers suggests a lunar recession rate significantly lower than today's value, consistent with models that predict faster recession when the Moon was closer and the tidal effects were stronger, but also sensitive to the paleogeography of the early Earth. Similar but younger archives exist in the Big Cottonwood Formation of Utah, roughly 900 million years old, and the Alatina Formation of South Australia, approximately 620 million years old. Each formation provides a different window into the past, a different constraint on how the Moon's distance has evolved. Taken together, these geological proxies reveal a recession history that is complex rather than simple, punctuated by changes in rate that reflect the dynamic nature of Earth's surface rather than the constant physics of tidal friction. The ranging data provide the anchor for this historical reconstruction, the modern baseline against which all other measurements are calibrated. Without knowing the current recession rate precisely, interpreting the geological evidence would be guesswork. With the 3.8 centimetres per year firmly established, researchers can project backward with confidence, testing models against the geological constraints, rejecting hypotheses that fail to match the observations. This interplay between precise modern measurement and careful geological reconstruction exemplifies how science advances not through single brilliant insights, but through the patient accumulation and integration of evidence from many sources. The ranging physicists firing lasers at the Moon and the field geologists crawling over outcrops in the Australian desert are engaged in the same project, both trying to understand how the Earth-Moon system has evolved over billions of years. Their tools are different, their timescales are different, but their questions converge on the same fundamental reality. The measurements have also enabled increasingly precise tests of conservation laws that physicists hold sacred. Angular momentum, conservation predicts a specific relationship between Earth's slowing rotation and the Moon's increasing orbital energy. Measure the rotation slowdown, measure the orbital expansion, and the two must match within the precision of the data. They do match, beautifully, confirming that no angular momentum is mysteriously appearing or disappearing from the system. Energy conservation makes similar predictions, and those too are confirmed. The Earth-Moon system serves as a working demonstration that the conservation laws discovered in laboratories apply equally to celestial mechanics, that physics is truly universal. These confirmations might seem like empty exercises, checking that the rules we already believe are true are in fact true. But such checks are essential. Physics advances not only by discovering new phenomena, but by testing established principles at ever greater precision and in ever more extreme conditions. Each confirmation builds confidence. Each anomaly, should one ever appear, would revolutionize our understanding. The ranging measurements sit at the intersection of gravitational physics and precision metrology, testing Einstein's equations in a regime that laboratory experiments cannot access. The instruments continue their patient work, night after night, year after year, accumulating the data that will enable ever more precise determination of how quickly the Moon retreats. Future improvements are planned and in some cases already being built. Next-generation retroreflectors with reduced thermal distortion and improved dust resistance may be deployed on upcoming lunar missions. Ground-based systems with even better timing resolution and signal-to-noise ratios are under development. The precision that today stands at 1 millimetre may improve to a fraction of a millimetre within the next decade. These improvements matter not for their own sake, but for what they enable. Better ranging precision allows better tests of gravitational physics. Better constraints on lunar recession allow better reconstructions of Earth's geological and climatic history. Better understanding of tidal dissipation allows better predictions of how the system will evolve into the future. The millimetres matter because they encode information that cruder measurements cannot extract. The measurement campaign represents something remarkable about human civilization, our ability to sustain complex scientific projects across generations, to maintain instruments and protocols over timescales that exceed individual careers, to accumulate knowledge through the patient work of many hands across many decades. The Apollo astronauts who deployed the first retroreflectors could not have imagined the precision that their instruments would eventually enable. The engineers who built the first ranging systems could not have predicted that the experiment would still be running half a century later, and the scientists who fire lasers at the Moon tonight cannot know what discoveries their distant successors will extract from the data they are currently collecting. This multi-generational aspect of lunar ranging echoes the multi-generational timescales of the recession itself. Just as the Moon's departure unfolds across eons that no individual human can perceive directly, the measurement of that departure unfolds across decades that no individual career can span. Both require thinking beyond the immediate, situating the present moment within a longer arc of change. Both demonstrate that significance often accumulates in increments too small to notice individually, but too large to ignore collectively. The retroreflectors on the lunar surface will eventually cease to function. Dust accumulation will render them effectively useless, or the optical materials will degrade beyond recovery, or the arrays will simply be lost to some unforeseen lunar surface process. When that happens, future missions will need to deploy replacements if the ranging campaign is to continue. The instruments we have placed on the Moon are not permanent any more than the Moon itself is permanent, not eternal any more than the Earth is eternal. They participate in the same universal impermanence, the same flow toward endings that the recession itself embodies. But while they function, they provide something extraordinary: direct perception of processes that ordinarily exceed human grasp. Through the medium of laser light and precise timing, we can feel the Moon receding, can watch the numbers change year by year, can verify that the physics we have deduced from theory corresponds to the reality of actual motion through actual space. The gap between calculation and observation closes. The abstract becomes concrete. The imperceptible becomes measured. This achievement deserves recognition as one of the great accomplishments of 20th and 21st century science. Not dramatic in the way of particle accelerators or space telescopes, not glamorous in the way of planetary exploration or gravitational wave detection, but foundational in a deeper sense. The ranging measurements demonstrate that we can track celestial motions with precision that our ancestors would have considered magical, that we can verify the equations of physics against the behaviour of actual worlds, that we can extend human perception to encompass changes that unfold across timescales vastly longer than any human life. The Moon recedes. We watch it go. We measure each centimetre of its departure, each millimetre of its slow drift outward into the darkness. The measurement itself becomes a kind of attention, a form of sustained awareness directed at a phenomenon that most people never consider. In measuring the recession, we honour it, acknowledge it, incorporate it into our understanding of what the Moon means and how our place in the cosmos continues to change. The tools reveal what the senses cannot detect, and in that revelation lies a deepening of our relationship with the sky, a transformation of the familiar into the genuinely understood. Yet understanding the recession is not the same as accepting what it means. The measurements confirm the physics, the retroreflectors track the departure, the equations predict the trajectory with exquisite precision. We know with a certainty that previous generations could never have achieved exactly how the Moon will move and when it will cross the thresholds that matter. But knowledge and acceptance inhabit different territories of the human mind. To truly grasp what the lunar recession means requires sitting with implications that resist comfortable accommodation, requires following the trajectory not just through space, but through consequence, requires asking what the departure of the Moon will eventually cost, and whether that cost carries meaning beyond the merely astronomical. The total solar eclipse stands as perhaps the most profound visual phenomenon available to human observers without technological assistance. When the Moon passes precisely between Earth and Sun, when its apparent size matches the solar disk with eerie exactness, the universe performs a transformation that transcends ordinary experience. Day becomes night in minutes. The temperature drops perceptibly. Birds fall silent or begin their evening songs in confusion. The corona, that ethereal halo of plasma extending millions of kilometres from the solar surface, becomes visible to the naked eye for the only time outside of total eclipses. Shadow bands ripple across the landscape in the final moments before totality. The quality of light shifts through shades that exist nowhere else in human visual experience, a twilight that belongs neither to dawn nor dusk, but to something entirely other. Throughout recorded history, total solar eclipses have inspired awe, terror, religious revelation, scientific discovery, and artistic creation. Ancient peoples interpreted them as divine interventions, as battles between celestial powers, as omens of disaster or transformation. The Chinese word for eclipse contains the character for eating, reflecting the myth that a dragon was consuming the sun. The Vikings believed wolves pursued the sun and moon across the sky, occasionally catching and devouring them. Across cultures and centuries, the sudden disappearance of the sun struck observers as an event requiring explanation, demanding interpretation, exceeding the boundaries of ordinary understanding. Modern science has stripped eclipses of their supernatural significance but not their emotional power. We understand now that the moon simply blocks the sun, that the alignment follows entirely from orbital mechanics, that the phenomenon carries no cosmic message and requires no mythological explanation. Yet this understanding does not diminish the experience. If anything, it deepens it. To stand beneath a total solar eclipse knowing what causes it, understanding the orbital dynamics and the physical optics and the precise geometry that creates this moment, adds a layer of wonder rather than subtracting one. The universe requires no supernatural intervention to produce experiences of transcendent beauty. The ordinary operation of gravity and light and planetary motion suffices. And that sufficiency itself carries a kind of meaning that no mythology could provide. The corona reveals itself only during totality because the sun's surface brightness normally overwhelms its diffuse outer atmosphere. The photosphere, that relatively thin layer from which most sunlight emanates, shines with an intensity that renders the corona invisible under ordinary circumstances. Even the best artificial coronagraphs, instruments designed to block the solar disk and reveal the corona, cannot match the precision of the lunar occultation. The moon's limb, that jagged edge of mountains and craters silhouetted against the solar surface, creates a natural mask of unparalleled accuracy. Through this mask, scientists have studied the corona, discovered helium, verified general relativity, and investigated solar physics in ways that no other method permits. Arthur Eddington's famous 1919 eclipse expedition measured the bending of starlight by the sun's gravitational field, providing early confirmation of Einstein's general theory of relativity. The experiment required a total solar eclipse because only during totality do stars near the sun's position become visible. The results, announced to great fanfare later that year, transformed Einstein from an obscure physicist into an international celebrity and established general relativity as the correct description of gravity. Without the moon's precise occultation of the solar disk, without the corona revealing totality that cleared the way for starlight to be photographed so close to the sun, this confirmation would have been vastly more difficult, if not practically impossible. The history of science contains numerous examples of total solar eclipses enabling discoveries that advanced human understanding of the cosmos. The chromosphere, that thin layer of the solar atmosphere between the photosphere and corona, was first studied during eclipses. Spectroscopic analysis of eclipse light led to the discovery of new elements and the understanding of stellar composition. The precise timing of eclipse contacts has refined our knowledge of the moon's orbit and the Earth's rotation. Each eclipse has offered opportunities that exist nowhere else in observational astronomy. And all of this depends on a coincidence that will not last. The moon's angular diameter currently averages about 31 arc minutes, varying slightly due to the elliptical shape of its orbit. The sun's angular diameter averages about 32 arc minutes, also varying with Earth's orbital position. The near equality of these values creates the conditions for total eclipses. When the moon stands at or near its closest approach to Earth and the sun at or near its greatest distance, the lunar disk can fully cover the solar disk with a margin to spare, creating totalities lasting up to about 7.5 minutes. When the geometry is less favourable, the moon still covers the sun but for shorter durations, sometimes only seconds of totality before the brilliant photosphere reappears. The recession erodes this margin relentlessly. Each year's 3.8 centimetres increases the Earth-Moon distance and decreases the moon's apparent angular diameter by an amount too small to notice, but too real to ignore. The shrinking proceeds at roughly 3/10,000ths of an arc-second per year, a change that requires centuries to accumulate into anything perceptible, but that compounds inexorably across the deep time ahead. The mathematics permits no ambiguity. The angles converge toward a threshold beyond which the geometry fails, beyond which the moon's disk can no longer span the sun's disk, regardless of orbital positions. That threshold lies roughly 600 million years in the future. The precision carries substantial uncertainty, because the recession rate itself will likely evolve as Earth's geography changes, as continents drift into new configurations, as ocean basins reshape and tidal dissipation patterns shift. But the order of magnitude is secure. Hundreds of millions of years from now, the last total solar eclipse will occur on Earth. After that moment, the moon will never again fully cover the sun as seen from our planet's surface. The cosmic coincidence that has graced Earth for hundreds of millions of years will end, and no purely natural process will restore it. 600 million years defies intuition. The span exceeds human comprehension, not by a small factor, but by an overwhelming one. 100 human lifetimes barely reach 10,000 years. 1,000 human lifetimes approach 100,000 years, still less than 1% of 1% of the time remaining. The entire duration of human existence, from the first members of our species walking the African savanna to whatever distant descendants might still call themselves human, will likely represent only a tiny fraction of the time before the last eclipse. We cannot feel 600 million years any more than we can feel the recession itself. Both exceed the temporal resolution of human experience by factors so large that the numbers become abstract, become symbols rather than quantities, become placeholders for durations that no consciousness like ours can genuinely encompass. Yet the meaning persists despite the incomprehensibility of the timescale, something that has always existed within human experience, something that has shaped religion and science and art and culture since before written records began, will eventually cease to exist. The total solar eclipse will join the category of phenomena that once occurred but no longer do, phenomena that future beings might read about in ancient records but will never witness for themselves. The experiential connection will sever. The direct encounter will become impossible. Whatever inherits the Earth in that distant era will know total eclipses only as historical artifacts, as descriptions in texts, as reconstructions in simulations, never as lived realities. This impending loss invites reflection on what total eclipses mean beyond their scientific utility. The utilitarian value, while significant, does not exhaust their importance. Eclipses have served science well, but they have also served something else, something harder to name but no less real. They have provided moments of collective wonder, experiences that connect individual observers to cosmic scales, encounters with the sublime that require no belief and no interpretation, only presence. The eclipse does not need to mean anything in order to matter. Its occurrence suffices. The shadow sweeping across the landscape, the corona blazing into visibility, the impossible sight of darkness where the sun should be. These experiences carry weight independent of any significance we might assign them. The photographers who travel thousands of miles to stand in totality's narrow path, the amateur astronomers who plan years in advance for a few minutes of observation, the casual tourists drawn by curiosity to experience what others describe as life-changing. All of them participate in something that the recession is slowly ending. They witness a phenomenon that their distant successors will not be able to witness, capture images that future generations will be able only to envy, feel emotions that the geometry of the future will not permit. In this sense, every total eclipse that now occurs carries a weight it did not carry before we understood the recession. Each totality becomes more precious precisely because we know the supply is finite, precisely because we can calculate how the resource will eventually exhaust itself. The preciousness does not depend on the shortage becoming acute within any living person's timeline. We need not personally experience the last eclipse for its approach to matter. The mere knowledge that such a last eclipse will occur, that somewhere in Earth's future lies a moment after which no human or posthuman or alien visitor will ever stand in the moon's full shadow, transforms how we might regard the eclipses we can still witness. They become not merely astronomical events, but historical events, moments positioned along a trajectory that has an end, gifts from a cosmic configuration that will not persist forever. The recession makes eclipses tragic in the original sense of that word, bounded, mortal, moving toward an inevitable conclusion that no intervention can prevent. But here the scale of deep time introduces a strange twist that almost qualifies as comfort. 600 million years is not merely long. It is long enough to contain essentially infinite contingency, long enough to render almost any prediction about Earth's future effectively meaningless, long enough that the loss of total eclipses ranks among the least of the changes that will transform this planet beyond recognition. The sun itself will have brightened sufficiently in 600 million years to raise significant questions about whether complex life can persist on Earth's surface. The carbonate-silicate cycle that has regulated Earth's climate for billions of years may reach limits beyond which atmospheric carbon dioxide falls too low for photosynthesis, potentially collapsing the biosphere as we understand it. Continental drift will have completely rearranged Earth's geography multiple times, creating and destroying ocean basins, raising and eroding mountain ranges, rewriting the maps we now consider permanent. In this context, Mourning the loss of total eclipses seems almost quaint, like worrying about the wallpaper in a house that is slowly burning down. Whatever entities exist on Earth in 600 million years, if any exist at all, will face challenges so far beyond our current concerns that the absence of total solar eclipses will likely not even register among their priorities. The recession proceeds within a larger envelope of change that dwarfs it, a transformation of the entire Earth system that will leave nothing familiar in its wake. The Moon's departure represents one thread in a tapestry of alterations so comprehensive that the tapestry itself will become unrecognisable. And yet the comparison cuts both ways. The very fact that so much else will change does not diminish the significance of the Moon's recession. Instead, it illuminates a truth about significance itself. Meaning does not require permanence. Value does not require eternity. The fact that everything transforms, that nothing endures unchanged across the full span of cosmic time, does not render the temporary unimportant. If it did, then everything would be unimportant, since nothing survives forever, not stars, not galaxies, not the universe itself in any configuration we would recognise. To require permanence as a condition of mattering is to demand something the cosmos cannot provide, and to condemn all existence to meaninglessness in the process. The alternative approach grants meaning to the transient precisely because it is transient. The total eclipse matters not, despite its eventual impossibility, but because of it. The bounded nature of the phenomenon, the knowledge that it exists within limits, the awareness that the cosmic accident enabling it has already begun to fail, these qualities enhance rather than diminish what the eclipse offers. A gift given once and never again carries different weight than a gift given endlessly. A phenomenon that will cease demands different attention than a phenomenon guaranteed to persist. The recession teaches this lesson through slow demonstration, through the patient accumulation of centimetres that will eventually sum to a fundamental change in what the sky can offer. This perspective transforms the lunar recession from a topic of astronomical interest into a meditation on impermanence itself. The Moon departs, the Earth slows, the eclipses dwindle, and will eventually fail entirely. Nothing about this trajectory can be reversed by any power humanity might plausibly wield. We can only observe, measure, understand, and accept. But acceptance need not mean resignation. It can instead mean appreciation, a deepened recognition of what exists while it exists, a commitment to experiencing and preserving what the present offers before the present becomes past. Consider the photographs of totality that already fill human archives. The black disk surrounded by the pearly corona, the stars emerging in artificial night, the landscape beneath the shadow rendered alien and strange. These images document something that future beings might never see directly, something that the geometry of the cosmos will eventually prohibit. They become not merely records but relics, artifacts of a configuration that once permitted wonders the future will not contain. Every photograph of a total eclipse now serves double duty: scientific datum and historical testimony, evidence of physics and memorial of possibility. The same applies to human memory of eclipse experience. Those who have stood in totality carry something irreplaceable, not just the memory of an event, but participation in a phenomenon that will not persist forever. Their experience joins a chain of similar experiences stretching back through human history, a chain that will eventually end when the geometry fails. To have witnessed totality is to have glimpsed something that exists on borrowed time, something that the patient work of gravity and angular momentum is slowly subtracting from Earth's endowment of wonders. This awareness need not lead to despair. The appropriate response to transience is not sorrow, but presence, not mourning, but attention. The Moon is still there tonight, still reflecting sunlight across the void, still raising tides and anchoring rhythms and preparing for future eclipses that will occur with all the drama and beauty of eclipses past. The recession has not yet succeeded in removing anything that humans have ever known. The process merely proceeds, as it has proceeded for 4.5 billion years, as it will proceed for billions more if the Sun's expansion does not intervene. Within human timescales, the Moon remains our companion, our fellow traveller, our familiar face in the sky. But familiarity deserves to be earned through understanding. The Moon that most people glance at without thinking contains depths that reward investigation, complexities that reveal themselves to careful attention, Stories that unfold across timescales almost too vast to comprehend. The recession is one such story. The tidal interaction that drives it connects us to physics at the most fundamental level, to energy conservation and angular momentum, and the behaviour of gravity across varying distances. To know about the recession is to know something real about how the cosmos operates, to hold in mind a truth that most people never encounter, and to feel that truth, to let it move from abstract knowledge into something approaching emotional reality, requires sitting with it, dwelling within it, allowing its implications to unfold without rushing toward resolution or comfort. The moon recedes, the moon recedes. Repeat it until the words begin to carry weight. 3.8 centimetres per year, a rate slow enough that mountains form and erode, that species evolve and go extinct, that entire civilizations rise and fall between noticeable increments, yet relentless, yet certain, yet already responsible for changes that have profoundly shaped Earth's history and will continue shaping its future until the story concludes in whatever distant configuration awaits. The Earth of 4.5 billion years ago lived beneath a moon 4 times closer than the moon of today. The tides that surged across that early world dwarfed anything the present oceans produce, racing across landscapes we would not recognise, carving channels through rocks that have long since subducted into the mantle or weathered into sand. Days raced by in hours rather than the stately 24 hours we now consider natural. The moon loomed vast in the sky, a presence so dominant that no observer could have ignored it. That world is gone, erased by the slow work of recession and rotation, and the million other processes that remake planets across deep time. We cannot visit it. We can only reconstruct it through the patient work of science, through the accumulation of evidence that reveals what once was. The Earth of 600 million years hence will likewise exist only in imagination for now, a world we can project but not know, can calculate but not experience. The moon will hang smaller in that sky, the days will stretch longer, the tides will run weaker, and the total eclipse will have passed into history. Whatever beings observe that sky, if any do, will inherit a cosmos that has moved on from configurations we consider normal, a cosmos that has forgotten the particular accident that once made our eclipses possible. They will have their own sky, their own phenomena, their own causes for wonder or indifference. But they will not have what we have. The coincidence will have expired. Between that past and that future stretches the present, the only moment we can actually inhabit, the only configuration we can actually witness. The moon stands tonight where it stands, not where it stood 1 billion years ago, not where it will stand 1 billion years hence, but where the patient accumulation of seconds has currently placed it. The recession continues as we speak, as we think, as we turn these thoughts in our minds. 3.8 centimetres closer to next year's position, 3.8 centimetres farther from last year's position, a movement so small that no human sense could detect it, but so real that laser light reveals it with perfect clarity. This is what it means to live on a changing world, orbiting a changing star within a changing cosmos. Nothing holds still, nothing persists unchanged. The familiar proves temporary on long enough timescales, and the timescales prove long enough for any transformation you might imagine. The moon was not always there in the form we know it. The moon will not always be there in the form we know it. But tonight, the moon is exactly there, exactly itself, exactly the companion Earth has known throughout all of human history, exactly the face our ancestors watched wax and wane, exactly the body whose shadow has swept across continents since before our species existed. The recession does not diminish this. If anything, it deepens it. Transience grants weight to presence. The knowledge that something will not last forever invests each moment of its existence with significance it would not otherwise carry. The moon will eventually drift beyond the reach that enables total eclipses, will eventually hang small and distant in a sky we cannot predict, will eventually become something other than what we have known. But the moon has not done these things yet. The moon remains, the moon abides, the moon rises tonight as it rose last night and will rise tomorrow night, patient and bright and marked with the same dark Maria that have stared down at Earth since long before eyes evolved to see them. Look up. The invitation is simple and requires nothing you do not already possess. Look up at the moon when it rises, when it sets, when it hangs at its apex burning white against the black. See it not as furniture of the sky, not as mere background to your terrestrial concerns, but as the drifting world it actually is, the departed fragment spiralling slowly outward, the companion whose departure proceeds so gradually that 1,000 human generations will notice nothing while the distance doubles. See the craters that record billions of years of bombardment, the rays that streak across the surface from impacts millions of years old, the Terminator line where day meets night in the sharpest division the solar system offers. See the body that causes your tides, that stabilizes your axis, that has shaped your history and your biology and your culture in ways too numerous to catalogue. And know, as you see it, that you're watching something in motion. Not the rapid motion of rising and setting, which merely reflects your own planet's rotation, but the slower motion that no night of watching could reveal. The drift, the departure, the 3.8 centimetres that accumulate while you sleep and wake and sleep again. The recession that connects this moment to moments billions of years past and billions of years future, that writes your present into a story so vast that you cannot perceive more than a single frame. The moon does not care about your watching. The moon has no awareness to care with, no intentions to fulfill, no knowledge of observation or meaning. The moon simply moves as gravity and momentum dictate, following physics with perfect fidelity, obeying laws that admit no exception and require no consciousness. The recession is not a choice. It is not a message. It is not aimed at anyone or anything. But your watching matters nevertheless. Your awareness transforms the phenomenon without altering it. The moon's recession is one thing when no one knows about it, another thing when conscious beings measure and understand it. The recession itself does not change, but its place in the web of meaning shifts when minds attend to it. You become the universe knowing itself, the cosmos contemplating its own mechanics, the process examining the process. This capacity for self-reflection distinguishes conscious observers from the unconscious matter that composes most of existence. The moon cannot wonder at its own recession. You can. And in wondering, in measuring, in following the patient accumulation of centimetres across years and decades and centuries, you participate in something extraordinary. You extend human perception beyond its natural limits. You feel, however indirectly, however abstractly, the actual motion of worlds through actual space across actual time. The gap between human senses and cosmic reality narrows. The universe becomes slightly less alien, slightly more known, slightly more incorporated into the growing body of what our species understands. The moon rises, the moon recedes, the equations predict, and the lasers verify, and the knowledge accumulates across generations of patient observation. Tonight the moon is where it is, and tomorrow night it will be imperceptibly farther, and the night after that farther still, and so on across a future so long that the numbers lose meaning, until eventually, impossibly far from now, the moon crosses a threshold, and something that has always been possible becomes impossible, and the total eclipse passes from experience into memory, from memory into history, from history into the fading records of a species that may itself have passed beyond recognition. But that ending does not diminish this beginning. That future does not devalue this present. The moon is still there. The moon is still ours, in the only sense that any cosmic body belongs to the small beings who observe it and wonder at it, and measure its patient departure. The familiar face in the sky remains familiar for now, for tonight, for all the nights that comprise a human life, and all the lives that comprise a human era. The moon drifts. We watch. The watching is enough.